The process for Almond Joy bars begins with the raw ingredients: shredded coconut, corn syrup, sugar, and water. These materials are fed into a high-capacity mixing vessel where large paddles rotate continuously to combine them into a dense, sticky coconut paste. The paste is heated as it mixes, reaching a precise temperature to ensure optimal moisture content and consistency. Steam jackets surrounding the mixing drum maintain uniform heat distribution. After several minutes of agitation, the mixture transforms into a glossy, pliable mass. This coconut blend is discharged onto a stainless steel conveyor, forming a continuous sheet. Guillotine cutters then divide this sheet into uniform, rectangular slabs. These slabs move onto a cooling tunnel, where chilled air circulates above and below the conveyor to reduce the temperature rapidly. Once cooled, the slabs gain structural integrity for the next phase. An automated depositor accurately places 2 whole, roasted almonds on top of each coconut piece. The almonds are fed from a vibratory feeder that singulates and orients each nut before placing them. Optical sensors verify almond placement, rejecting any slabs with missing or misaligned nuts. The spacing between slabs is synchronized with the timing of the almond dispenser to ensure precise application. After almond placement, the coconut almond assemblies enter the enrobing line. They travel on a wire mesh belt into the chocolate enrober. Here, tempered milk chocolate is pumped from a holding tank and cascades in a curtain over the products. Simultaneously, bottoming rollers coat the underside, while air blowers above the curtain remove excess chocolate to create a uniform layer. The temperature and viscosity of the chocolate are controlled precisely to ensure an even coat without streaks or pooling. Next, the enrobed bars pass through a vibrating section that settles the chocolate and removes air bubbles. Then they enter the cooling tunnel. This refrigerated section spans over 20 meters and contains multiple zones, each with slightly different temperatures. The chocolate solidifies gradually, preventing cracking or bloom. Infrared sensors monitor the cooling progress, and conveyor speed adjusts dynamically to match ambient conditions and chocolate thickness. Once fully cooled, the bars exit the tunnel and proceed towards the wrapping station. Before wrapping, laser scanners inspect each piece for weight, shape, and coating quality. Any defective bars are automatically diverted. Accepted products enter the flow wrapping machine. Foil film unwinds from a large roll, guided through tension rollers and over-forming boxes that shape the film into a continuous tube around the bars. As the bars advance, a longitudinal heat seal bar bonds the foil edges beneath each piece. Rotary cross-sealed jaws then crimp and seal the ends while simultaneously cutting between products. This continuous process wraps hundreds of bars per minute. Coded inkjet printers apply date and batch information onto each wrapper before they drop into sorting lanes. From here, robotic arms pick and place the wrapped bars into pre-formed trays. These trays are die-cut from cardboard sheets and folded by a tray former, using glue and pneumatic pressure. As bars fill the trays, they move onto a cartoning line. An overhead magazine feeds folded cartons downward into a conveyor slot. Mechanical pushers load each filled tray into a carton, which is then closed by hot melt glue nozzles and compressed by rollers to seal. Final cartons advance to the case packing station. A pick-and-place robot, using vacuum suction cups, lifts multiple cartons at once and stacks them inside corrugated cases. These cases are pre-erected by a case-forming unit, which folds and glues flat blanks into box shapes. Once filled, each case is sealed with tape or glue and weighed automatically to confirm count accuracy. Any discrepancies result in automatic rejection to a separate line. The sealed cases move onto a palletizer. This system includes a conveyor with metering belts that space the cases evenly. A robotic palletizer arm, guided by a vision system, arranges the cases in a specific pattern on wooden pallets. Slip sheets may be inserted between layers to increase load stability. Once a full pallet is formed, it is wrapped with stretch film by a turntable or rotary arm wrapper. The tension of the film is adjusted to hold the load tightly without crushing the contents. Meanwhile, upstream in the process, the almonds used for topping are also processed on site. Raw almonds are first poured into a hopper and elevated via a bucket conveyor into a dry roaster. The roaster rotates continuously, exposing the nuts to hot, dry air for uniform roasting. A cyclone exhaust system removes smoke and particulates. Once roasted, the almonds fall into a vibrating cooling tray where fans draw ambient air across them to bring them down to room temperature. An optical sorter then inspects the almonds. Using cameras and ejector nozzles, the system identifies any discolored, damaged, or misshapen nuts and removes them with puffs of air. Accepted almonds are stored in stainless steel bins and delivered via pneumatic tube to the depositor above the coconut slab line. Coconut preparation also begins earlier in the process. Desiccated coconut flakes arrive in bulk and are fed into a sifting machine to remove clumps or foreign particles. The flakes then enter a rotary drum blender, where they are pre-mixed with a portion of syrup before being transferred to the main mixing tank. This pre-blending step improves consistency and reduces processing time during the main blend. The chocolate used for enrobing is stored in large insulated tanks fitted with agitators. These tanks keep the chocolate at a precise temperature, around 45 degrees Celsius before tempering. Chocolate flows through jacketed stainless steel piping to the tempering unit. This unit lowers the temperature in stages using heat exchangers, forcing the formation of stable cocoa butter crystals. Proper tempering ensures the finished coating has a glossy sheen and crisp snap. A constant flow meter and feedback loop regulate chocolate volume to the enrober, ensuring the curtain maintains consistent thickness. Excess chocolate that falls through the wire mesh belt is captured in a trough and recirculated back to the holding tank, filtered through a mesh screen to remove debris. The enrobing line operates in tandem with the cooling tunnel. If the cooling tunnel temperature deviates even slightly, sensors trigger a feedback loop that adjusts the chocolate flow or pauses the feed conveyor. This ensures consistent coating quality regardless of fluctuations in humidity or external temperature. In parallel, the packaging materials are staged continuously. Foil film for wrapping is mounted on automatic splicing unwinders. When one roll nears its end, the splicer joins it to the leading edge of the next roll without stopping the machine. The new roll then feeds in seamlessly, avoiding downtime. Carton blanks are similarly auto-loaded into magazines from a central storage station using robotic arms. Inkjet printers that mark each wrapper with date codes and batch numbers are calibrated periodically by automated test patterns. Vision systems confirm legibility and alignment. Any misprints trigger alerts and divert the affected bars before case packing. Throughout the entire process, programmable logic controllers, PLCs, synchronize every machine on the line. Conveyor speeds, cutter intervals, depositor timing, and wrapping cycles all respond in real time to upstream and downstream data. If any single machine slows down or stops, the line adjusts automatically to prevent product buildup or jams. The entire system is designed for continuous flow. Changeovers, such as switching from one packaging format to another, are done with modular tooling. Quick release components and digital recipe settings allow for rapid reconfiguration without manual recalibration. The final stage involves labeling the wrapped pallets. Each finished pallet passes through a print and apply labeler that adheres a shipping label containing product type, quantity, and a scannable barcode. Pallets then queue for loading onto transport vehicles, completing the production cycle. Production begins with the core element of the Butterfinger bar, a crisp, flaky peanut butter candy center. The process starts by preparing the peanut butter base. Roasted peanuts are fed into a heavy-duty grinder, where rotating steel blades reduce them into a fine, smooth paste. This peanut butter is pumped into insulated holding tanks kept at a stable temperature to maintain flowability and prevent separation. Simultaneously, corn syrup and sugar are combined in a large stainless steel batch cooker. High-pressure steam heats the mixture, raising the temperature rapidly to reach the soft crack stage, approximately 270 degrees Fahrenheit. Agitators keep the syrup moving, ensuring even heating and preventing scorching. Once the desired temperature and consistency are achieved, the molten sugar mixture is discharged onto a temperature-controlled transfer belt. At this stage, the peanut butter from the holding tanks is precisely metered and deposited onto the hot sugar mass. The two components are folded together using automated paddles on a wide sheeting line. The mixture is not blended fully. Instead, it is laminated through a process that stacks and folds the layers repeatedly. This mechanical lamination is essential to achieve the signature crisp, flaky texture. Dozens of folding rollers repeatedly compress and layer the candy sheet, similar to how puff pastry is created, but on a large industrial scale. The candy sheet moves through gauge rollers that compress it to a uniform thickness. Guillotine-style cutters slice the sheet into long, narrow slabs. These slabs are transferred onto a chilled conveyor, where ambient air and refrigeration coils bring the internal temperature down quickly to stabilize the structure. This chilling also prevents further softening and locks in the laminated texture. Next, the slabs enter a precision cutter that slices them into bar-sized segments. High-speed rotary knives make clean cuts without fracturing the delicate, layered interior. Each segment now forms the crisp, candy center of the Butterfinger bar. These centers are transferred via a vibratory conveyor to the enrobing station. Before entering the enrober, the bars pass under a de-dusting system, which removes surface crumbs using vacuum suction and a soft rotating brush. This ensures smooth chocolate coating and prevents contamination of the chocolate supply. The enrobing process begins with tempered milk chocolate stored in heated tanks. Chocolate is pumped through jacketed pipes to maintain precise viscosity. It is delivered into the enrober, where it flows down a stainless steel curtain nozzle, forming a continuous sheet of chocolate over the moving bars. A bottoming roller coats the underside as the bars glide across a wire mesh belt. Top-mounted air knives blow away excess chocolate, ensuring an even, glossy finish. The freshly coated bars move into a cooling tunnel immediately after enrobing. The tunnel is divided into multiple zones, each with independently controlled temperatures and airflow. The cooling begins gradually to avoid thermal shock, then increases in intensity to solidify the chocolate quickly. The belt moves slowly through the tunnel, allowing several minutes of uninterrupted cooling. As the bars exit the tunnel, they undergo a multi-point inspection. Vision systems equipped with cameras check each bar for coating uniformity, alignment, and surface finish. Any bar that fails inspection is automatically removed by a pneumatic pusher. Approved bars enter the wrapping line. A foil film roll unwinds over a forming plow, folding around each bar as it moves down the line. A longitudinal heat seal bar closes the film beneath the bar, while rotary crimpers seal and cut the ends. Wrapping machines operate in synchronization with the enrobing line to maintain product spacing and alignment. Printed batch codes are applied to each wrapper by a high-resolution inkjet system positioned just after the crimper. Wrapped bars are conveyed to a collation station where they are grouped by count. A Delta-style robotic arm with suction grippers picks and places the grouped bars into open-top trays. These trays are formed upstream from flat blanks by a tray erector that folds and glues the cardboard using pneumatic arms and hot melt adhesive. Filled trays pass to a cartoning machine. An overhead feeder supplies flat cartons, which are opened and inserted with filled trays by servo-driven pushers. Cartons are sealed using precise glue nozzles and compressing belts. Each finished carton is marked with tracking and date codes using laser or thermal transfer printers. Completed cartons enter a case packer. A gantry robot equipped with a vacuum gripper picks up multiple cartons simultaneously and places them into corrugated shipping cases. These cases are pre-assembled by a case former and moved into position via indexing belts. Once filled, the cases are sealed with adhesive tape or glue. A print and apply labeler affixes a barcoded shipping label to each case. The sealed cases proceed to palletizing. A multi-axis palletizer arranges the cases in tiered patterns onto wooden pallets. Between layers, a slip sheet may be inserted to enhance load stability. Once the pallet is full, it rotates on a turntable as a mechanical arm wraps it with stretch film. The stretch wrapper adjusts film tension dynamically based on load weight and geometry, securing the entire structure for transport. Upstream in the production line, the chocolate coating undergoes constant temperature regulation. Tempering machines cool the chocolate in a staged process, forcing the crystallization of stable cocoa butter forms. This gives the final product a glossy finish and snap-resistant texture. Flow meters and viscosity sensors provide feedback to control loops that adjust pump speeds and heater output in real time. The laminated candy mass is one of the most technically distinct features of the production. The folding sequence uses custom roller configurations that alternate direction, speed, and pressure. Each fold adds to the internal complexity of the texture. A typical bar contains dozens of micro layers, giving it the distinct crispness when bitten. This structural design is sensitive to temperature, humidity, and mechanical handling, so the sheeting and folding areas are tightly climate controlled. The peanut butter used in the center is blended with sugar and other stabilizers before being layered with the syrup. This formulation is tested inline by viscosity sensors and refractometers that monitor sugar content in real time. If the mixture deviates from the programmed tolerance, the control system adjusts ingredient flow rates accordingly. To maintain the speed of output, the bar line operates in a modular configuration. If a segment of the system must be serviced, diverter arms can reroute product flow to a secondary line, allowing continuous operation. Every segment, cooking, sheeting, cooling, enrobing, and wrapping, can be isolated without halting the entire process. The cooling tunnels use variable speed fans and ducted airflow to tailor cooling intensity at each zone. Sensors measure product surface temperature and ambient humidity, feeding data back into the control system. As the bars pass from zone to zone, the belt may speed up or slow down slightly to maintain optimal crystallization and surface finish. Wrapping film splices are handled automatically. When a roll nears depletion, a sensor triggers a splicing unit that aligns and glues the new roll to the tail of the old one. The machine then trims the overlap without stopping the line. This keeps the wrapper feed continuous at speeds exceeding 300 bars per minute. Throughout the factory, PLCs and SCADA systems provide centralized monitoring. Every component, from syrup temperature to wrapper tension, is recorded and visualized on operator interfaces. Alarms, fault logs, and trend graphs allow rapid diagnostics and fine-tuning. M&M production begins with the creation of the chocolate centers. Liquid chocolate is prepared by mixing cocoa mass, cocoa butter, sugar, milk solids, and emulsifiers inside large jacketed mixing tanks. These ingredients are blended under controlled heat, while powerful agitators stir the mixture into a smooth, homogeneous fluid. The chocolate is then pumped into a conch, where granite rollers knead the mixture for several hours. This conching process reduces particle size and removes unwanted volatiles, refining both texture and flavor. Once conked, the chocolate is transferred to tempering units. These machines cool and reheat the chocolate in specific sequences to form stable cocoa butter crystals. Tempered chocolate flows into depositors positioned over a rotating stainless steel molding wheel. The wheel contains thousands of spherical indentations, each forming a uniform droplet of chocolate. As the wheel turns, each cavity is filled with a precise amount of liquid chocolate. Vibratory mechanisms remove air bubbles and level the surface. The molding wheel then passes through a refrigerated chamber where cooled air rapidly solidifies the droplets. After solidification, a mechanical arm ejects the chocolate cores from the molds onto a vibrating belt. These newly formed chocolate lentils, roughly elliptical in shape, move forward toward the panning line. The chocolate centers are conveyed into large stainless steel panning drums, tilted cylinders that rotate continuously. Dozens of panning drums operate simultaneously. Each is loaded with a specific quantity of chocolate centers. As the drums spin, sugar syrup is sprayed onto the tumbling chocolate pieces through fine mist nozzles. A thin film of syrup coats the surface of each piece. Air jets blow over the surface, drying the syrup into a hardened sugar layer. This syrup application and drying cycle repeats hundreds of times. Each repetition builds up the candy shell in ultra-thin layers. The panning operator adjusts nozzle spray rate, drum speed, and airflow volume according to the size and hardness required. Throughout the process, the chocolate centers maintain constant tumbling motion. This prevents clumping and ensures each piece receives uniform coating. After the desired thickness is reached, color application begins. Colored sugar solutions, each with precise pigment concentration, are sprayed onto the candy shells in sequential passes. Each batch receives only one color per drum. The pieces are again dried with warm air jets to solidify the surface. The entire color coding process is calibrated to maintain consistent hue, gloss, and shell thickness across every batch. Once the final colored layer is applied, the candies receive a polishing glaze. A food-grade wax solution is sprayed into the pan, and the candies tumble for several additional minutes. This glaze creates the familiar glossy finish. After polishing, the finished M&Ms are discharged through a sieve that removes any fragments or dust. A vibratory feeder lines the candies into single file for inspection. High-speed optical scanners evaluate every candy for size, color, accuracy, and shell integrity. Defective pieces, those with cracks, discoloration, or misshaped forms, are identified by vision systems and removed with bursts of compressed air directed through solenoid valves. Accepted candies move forward to the printing line. Here, each piece passes beneath a high-precision offset printing drum. The white M logo is printed using food-safe, edible ink. Registration sensors synchronize the rotation of each candy with the printing drum to ensure proper logo alignment. If a piece is misoriented, it is bypassed without printing and redirected for recirculation. Printed candies are conveyed into temporary buffer hoppers, where they accumulate in large quantities before packaging. From the hoppers, controlled feeders deliver exact quantities into multi-head weighers. These weighers use load cells beneath each head to measure candy mass with high accuracy. Microprocessors calculate the ideal combination of heads to reach the target weight for each package. Portioned candies drop into form-fill-seal packaging machines. Rolls of pre-printed plastic film unwind over forming collars, creating a vertical tube. The tube is sealed lengthwise by heated jaws, and the bottom is sealed just before the candy drops in. Once filled, another set of jaws closes the top, sealing and cutting the pouch simultaneously. Each sealed package drops onto a conveyor where inkjet printers apply batch codes and expiration dates. Pouches are then grouped by count and moved to the cartoning line. Flat carton blanks are fed into a cartoner, where rotary arms erect each box and load the required number of pouches. Hot melt glue nozzles seal the cartons closed as compression belts press the flaps together. Cartons then pass under a laser printer, which marks them with lot identification and traceability codes. From here, the cartons are transferred to a case packer. A Delta robot arranges them into patterns on corrugated trays or boxes. The case former erects these corrugated boxes from flat sheets, applies glue, and folds the flaps into rigid containers. Filled cases pass through a sealing station where tape heads or glue applicators close the top flaps. A print and apply labeler places barcoded shipping labels onto each case. Completed cases advance to a palletizing cell. Here, a robotic arm equipped with a vacuum or mechanical gripper stacks the cases layer by layer onto wooden pallets. An interleaving slip sheet may be inserted between each layer for added stability. Once a pallet is full, it moves into a stretch wrapper, where plastic film is tightly wound around the load in a spiral pattern. This secures the cargo for transportation. Upstream in the process, the chocolate preparation is a continuous operation. Chocolate mass is kept at steady viscosity using inline tempering loops that reintroduce flow from the depositor tanks back to the holding vessels. Viscosity meters, thermocouples, and pressure sensors feed data to PLCs, which adjust temperatures, stirrer speed, and flow rates in real time to match depositor demand. Sugar syrup for the shell coating is made in a separate station. Granulated sugar is dissolved in hot water under agitation in jacketed tanks. This syrup is filtered and stored in surge tanks equipped with inline heaters to maintain constant temperature. Syrup is piped to each panning drum via peristaltic pumps, which allow accurate dosing without pulsation. Color solutions are prepared in small batches using color concentrates blended with sugar syrup and stabilizers. Each pigment batch is tested for concentration and consistency using spectrophotometers before being pumped into the color panning drums. After use, nozzles and drum interiors are washed with a CIP, clean-in-place system that uses pressurized water and sanitizing agents to ensure no cross-contamination between colors. Each panning drum operates under its own programmable controller, allowing multiple colors to be produced in parallel. Drum speed, spray rate, and airflow parameters are automatically recorded and adjusted according to preset recipes. The polishing stage uses a blend of carnauba wax and other glazing agents stored in a heated tank and applied with atomizing nozzles. Excess polish is absorbed by the tumbling motion of the candies and distributed evenly across all surfaces. Drum rotation continues after spray ends, allowing full drying and shine development. Optical inspection uses high frame rate cameras positioned around the candy stream. Each camera captures images at over 1,000 frames per second. Software analyzes size, color uniformity, shape, and surface smoothness. Rejected candies are sent back through the coding line if salvageable or discarded automatically. Logo printing accuracy is ensured by aligning the candies in a channel that presents one face upward. Infrared sensors detect orientation. The offset drum presses the white ink M precisely where programmed, and vacuum assistance ensures stable contact during printing. The multi-head weighers used for portioning operate on combination logic. Each head dispenses a small, known weight of candy. The machine calculates the optimal combination of heads that adds up to the desired target weight, typically 1.69 ounces, 3.14 ounces, or other package sizes. Drop timing is synchronized with the pouch forming cycle to avoid spillage or sealing errors. Pouch film is fed through a series of tension rollers to keep it flat and aligned. Registration marks on the film are read by photoelectric sensors, which cue the sealing jaws and cutting blades to operate at exact positions. This ensures that every pouch has centered graphics and correct product display. The manufacturing process for Ruffles potato chips begins long before a potato even enters the production facility. It starts with agricultural planning and controlled sourcing. Ruffles, as a brand under Frito-Lay, utilizes proprietary potato varieties that are cultivated specifically for chip production. These aren't the same types of potatoes used for baking or mashing. Instead, Frito-Lay contracts with dozens of partner farms across the United States and other regions to grow chipping potatoes, varieties like Atlantic, Snowden, or proprietary Frito-Lay hybrids that are selected for their specific characteristics: high dry matter content, low sugar levels, uniform shape, and dense texture. Each crop is grown with tight controls on irrigation, fertilizer use, and harvesting schedules to ensure consistency and minimize storage degradation. Potatoes that are too moist, sugary, or irregular in shape would result in chips that are oily, dark, or fragile, none of which meet the Ruffles brand standard. At harvest, potatoes are collected using automated harvesters equipped with rubber conveyors that minimize bruising. They're loaded into transport trucks and sent to the factory, often within a few days of being pulled from the ground. When the potatoes arrive at the processing plant, they enter the facility through the raw receiving bay. These are enclosed intake areas where truckloads are weighed, logged, and tested before being accepted for processing. At this point, technicians from the quality assurance team extract random samples from the load to check for size uniformity, sugar content, starch levels, and moisture content. Any batch of potatoes that falls outside the tight specification window may be rejected or diverted to other non-chip product lines. Once cleared, the potatoes are offloaded from the trucks into a large receiving pit, essentially a hopper connected to a series of conveyor belts. From here, the potatoes are moved toward the initial cleaning phase. This begins with the destoning drum. As the potatoes enter this large rotating cylinder, jets of water and the rotating action cause heavier materials, like rocks or clumps of soil, to separate and fall through grated bottoms. Potatoes are lighter and are lifted to the next stage. From the destoning drum, the potatoes enter the pre-wash flume system. A flume is a water-filled channel that moves product gently using the flow of water instead of belts. This minimizes physical damage to the raw potatoes while removing dirt and loose debris. The flume water is treated and recirculated through industrial filters and chemical dosing systems to ensure both sanitation and water conservation. In many modern plants, the water used in these systems is part of a closed-loop recovery system designed to reduce environmental impact. The next stop is the rotary scrubber. This is a long, cylindrical machine fitted with internal brushes that rotate as the potatoes pass through. High-pressure nozzles spray water as the tub rotates, scrubbing away any remaining mud, sand, or biological debris. The inside of the scrubber is lined with abrasive surfaces that help clean the rough skin of the potato without cutting into the flesh. The goal here is to deliver a clean, undamaged potato with its skin still intact, ready for inspection. After scrubbing, the potatoes are lifted out of the washer by a cleated incline conveyor and passed through a visual and automated inspection system. In this phase, both human inspectors and camera-based vision systems work in parallel. The conveyor belt is engineered to spread out potatoes into a single layer, and each tuber moves past a combination of high-resolution cameras and infrared sensors. These systems are trained to detect green spots, bruises, cuts, or signs of rot. Any substandard potatoes are rejected via automated diverter arms or air jets, which remove the faulty items from the belt and send them to waste or compost streams. Human operators stationed along the line also remove visibly defective items that machines might miss, such as those with odd shapes that won't slice well on the crinkle-cut blades. Every removed potato is scanned and logged into the factory's waste tracking system, allowing operators to identify trends and address upstream sourcing problems if too many rejects appear from a single truckload. Now that the potatoes have passed visual inspection, they move on to the peeling station. For Ruffles, peeling is essential. While some gourmet-style chips retain their skins, Ruffles chips require a smooth, peeled surface to produce clean, consistent ridges during slicing. Peeling is achieved using a combination of steam and abrasion in what's known as a steam peeler. The steam peeler is a high-pressure vessel that receives a batch of potatoes, seals the chamber, and subjects the potatoes to pressurized steam, usually around 180-220 psi for 8 to 20 seconds. This superheated environment rapidly loosens the outer skin layer by partially gelatinizing the pectin between the skin and the underlying tissue. Once the steam cycle ends, a sudden pressure drop causes the skin to puff and detach slightly from the flesh. Immediately after this, the potatoes are discharged into an abrasive roller peeler. This is a rotating drum lined with rough surfaces, often embedded with carborundum grit, that gently scrubs the now loosened skins away. Water sprays are used to flush away the skins and clean the exposed potato surface. The amount of skin removed is carefully monitored. Too much abrasion would remove usable flesh and increase waste. Too little would leave patches of skin that affect the slicing process. The peeled potatoes are rinsed again in chilled water to stop any residual thermal activity and prevent enzymatic browning. A small dose of food-safe antioxidant, like sodium metabisulfite or citric acid, may be added to the rinse water to preserve the pale color of the peeled surface and prevent discoloration before slicing. At this stage, the potatoes are fully clean, peeled, and ready for their signature transformation, being cut into the iconic ridged slices that define a Ruffles chip. With the freshly peeled and rinsed potatoes now ready for transformation, the next phase in the Ruffles production process focuses on slicing, the moment where whole tubers are precisely cut into their distinctive ridged form. The ridges are far more than a visual or marketing detail. They play a critical role in the chip's strength, texture, and frying performance. This stage involves advanced slicing technology, careful temperature and starch control, and continuous monitoring to ensure each slice is the exact thickness, shape, and structural consistency required for optimal cooking and crispness. The peeled potatoes are transported to the slicing area via gentle, water-based flumes or soft conveyor belts to minimize impact and prevent bruising. Once they reach the slicing units, the potatoes are fed one by one into high-speed rotary slicers designed specifically for crinkle or corrugated cuts. These industrial slicing machines use a rotating impeller or feed wheel to press each potato firmly against a stationary, razor-sharp cutting head fitted with ridged blades. The blades are precisely machined to form a consistent wave pattern, typically with a wave amplitude of 1.5, 2.5 mm and a thickness of around 1.3, 1.5 mm. Unlike flat chip slicing, where a smooth blade is sufficient, Ruffles require a carefully engineered ridged blade made of hardened stainless steel. These blades are aligned at specific angles to produce even, undistorted waves along the chip's entire surface. The sharpness, speed of rotation, and pressure exerted must be perfectly balanced. Too much force or misalignment can result in chips with uneven ridges or broken tips, which would either fry unevenly or be rejected later during inspection. The sliced potatoes are ejected from the slicing drum at high velocity and collected in a shallow trough or on a belt that immediately begins the next critical step: starch removal and surface moisture control. Every potato contains natural starch, and when sliced, a large amount of that starch is released onto the cut surfaces. If not removed, this surface starch can interfere with the frying process, causing chips to stick together, fry unevenly, or develop burnt spots. It can also result in a greasy or gummy mouthfeel, which is unacceptable for Ruffles' clean, crisp texture. To remove excess starch, the slices pass through a multi-stage rinsing system. In the first phase, they enter a flume filled with cold, recirculated water, where they are gently agitated to dislodge free starch. The water in this flume is constantly filtered and monitored for starch content. with automated control systems adjusting flow rate and replacement intervals to maintain effectiveness. Following the first rinse, the slices often move through a series of cascading rinse curtains, sheets of filtered water that fall like waterfalls over the slices as they travel along a mesh or perforated conveyor belt. This helps remove residual starch without applying any mechanical force that could break the delicate ridges. After rinsing, the slices must be dried to a specific degree, not fully desiccated, but dry enough on the surface to allow the hot oil in the fryer to crisp the exterior without creating steam pockets or excessive foaming. This is achieved using a dewatering shaker and an air drying tunnel. The dewatering shaker is a vibrating belt or tray that shakes the slices gently to remove bulk water. The slices then pass under high-velocity air knives, rows of precisely aligned jets that blast room temperature or slightly warmed air across the chip surface. The air knives are tuned to create a shearing effect that strips away surface moisture while maintaining the shape and integrity of the ridged cuts. At this point, the slices are considered ready for frying, but only if they meet one final set of pre-cook inspection criteria. Before entering the fryer, the slices pass through an optical sorting system. This state-of-the-art inspection station uses a combination of high-resolution cameras, infrared sensors, and sometimes laser scanners to detect defects such as green spots, bruising, overly large slices, or broken pieces. Defective slices are rejected with microbursts of compressed air, which knock them off the main conveyor line and into waste or reprocessing bins. The acceptable slices, meanwhile, are evenly distributed across the width of the fryer in feed conveyor to ensure uniform exposure to hot oil. Frying is where the raw slices become what we recognize as potato chips. And for Ruffles, this step is both art and engineering. The chips are fried in continuous fryers, long stainless steel troughs filled with high-temperature cooking oil. The oil is typically a carefully formulated blend of vegetable oils, often including sunflower, corn, or canola oil, chosen for their high smoke points, neutral flavor, and oxidative stability. The oil is filtered, treated, and replaced on a tightly regulated schedule to maintain quality and avoid flavor degradation. As the slices enter the fryer, they are immediately submerged by a submersion conveyor that ensures they stay evenly beneath the oil's surface throughout the cooking process. The oil is maintained at a precise temperature, usually between 170 degrees Celsius and 190 degrees Celsius. This range is critical. Too cool, and the chips absorb oil and turn soggy. Too hot, and they brown too quickly or develop burnt notes. Each chip is cooked for approximately 2 to 3 minutes, depending on thickness, oil composition, and desired moisture content. Inside the fryer, the chips expand slightly and crisp as their internal water content rapidly evaporates. The ridged surface of Ruffles causes the chip to fry unevenly by design, creating micro variations in texture that result in a more substantial bite and greater structural integrity. The ridges also slow oil drainage, allowing a slightly longer dwell time that contributes to the chip's durability and resistance to breakage during dipping. The fryer is equipped with multiple sensors and flow meters that measure oil temperature, turnover rate, chip feed rate, and even in-oil moisture concentration. These data are analyzed in real time by the factory's central control system, allowing operators to make immediate adjustments. In many facilities, the frying process is linked to upstream slicing sensors. For example, if slightly thicker slices are detected coming from the cutter, the fryer conveyor speed is slowed accordingly to ensure proper cook time. As the chips emerge from the fryer, they pass through an oil draining phase. A vibrating conveyor with a perforated surface allows excess oil to drip off. This is immediately followed by an air cooling system that begins to lower the chip's temperature, halting further cooking and locking in texture. Cooling is essential not only for texture stability, but also to prepare the chips for seasoning, which happens shortly after. But before we get to seasoning, there's a critical interlude in the process: moisture analysis and inline quality control. At this stage, a small percentage of chips are diverted through a sampling chute to a nearby test station. Here, technicians use moisture analyzers, color meters, and even acoustic crispness testers to evaluate product characteristics. These tests ensure that the chips meet the factory's targets for final moisture content, color uniformity, and physical integrity. As the freshly fried and cooled Ruffles chips exit the fryer and pass through preliminary quality control, they enter one of the most dynamic and highly controlled stages in the factory: seasoning. This is the phase where the chips receive their final flavor identity, whether it's the original lightly salted variant, sour cream and onion, cheddar and sour cream, jalapeno ranch, or any of the other regional and seasonal flavor options Ruffles is known for. Applying these flavors evenly, consistently, and at high speed while preserving the chip's structural integrity and minimizing waste is a challenge that modern factories solve using specialized equipment and real-time process monitoring. The chips arrive at the seasoning station on a wide, inclined conveyor or vibratory tray that serves two main functions. It spreads the chips out into a single layer to prevent overlap, and it gently agglomerates chips to control their flow into the seasoning drum without damaging them. Due to the ridged shape and the thicker cut of Ruffles compared to standard potato chips, seasoning application must account for deeper surface area and variable orientation. Some chips will face ridge side up, some down, some angled. Seasoning application takes place inside a rotating tumbler drum, also called a flavor drum or seasoning cylinder. This stainless steel drum is set at a slight incline and constantly turns on its horizontal axis, gently lifting and tumbling the chips while they rotate through it. At the entrance to this drum, a continuous metered flow of seasoning powder is dispensed through an auger-based dosing system. The seasoning blend, pre-mixed according to a proprietary formula, includes a combination of salt, natural and artificial flavorings, cheese powders, dehydrated dairy, onion and garlic powders, spices, yeast extract, and anti-caking agents. The dosage rate of the seasoning is tightly controlled via real-time feedback systems. Optical sensors measure the chip volume entering the drum, and the dosing screw adjusts the delivery rate to maintain an ideal flavor to surface area ratio. Too much seasoning leads to clumping, over-salted chips, and waste. Too little results in bland or unevenly flavored chips that fail quality checks. For cheese-based seasonings, which are more moisture sensitive, the flow system may include a nitrogen-purged hopper or desiccant units to prevent clumping in humid environments. Inside the flavor drum, fine misting nozzles also spray a light coating of oil to help the seasoning adhere evenly to the chip surface. This atomized oil does not soak the chips, but rather creates a microfilm that holds the powder in place without compromising crunch. The rate of oil application, angle of spray, and temperature are all adjusted based on the type of seasoning used. For example, heavily coated varieties like cheddar and sour cream require more binder oil and a slightly longer tumbling duration to ensure every chip is fully and evenly coated. Throughout the seasoning process, line operators and quality assurance technicians take random samples every few minutes. These samples are assessed for seasoning coverage, color intensity, and surface powder levels. In more advanced factories, seasoning uniformity is checked with hyperspectral cameras that scan the chips as they exit the drum, detecting variations invisible to the human eye and triggering alerts or auto-calibration if inconsistencies are detected. Once the chips have been properly seasoned, they are transferred to the packaging phase. This is a highly automated and synchronized system that must meet several objectives simultaneously. Protect the chips from breakage, preserve freshness, prevent contamination, provide product information to the consumer, and maintain traceability for safety audits. Packaging begins with product accumulation. Conveyors from multiple seasoning drums may feed into a single accumulation hopper or weigher, depending on line configuration. This hopper temporarily holds chips before they're dispensed into individual bags via a multi-head combination weigher. A multi-head weigher is an advanced piece of equipment with multiple radial feed hoppers arranged in a circular pattern. Each hopper releases a small portion of chips, and a central computer instantly calculates which combination of hoppers adds up closest to the target weight, say 28.3 grams for a single serve bag. This combination is released simultaneously into a timing hopper, which drops the exact weight into a vertical form-fill-seal packaging machine. The VFFS machine forms bags from a continuous roll of printed plastic film, often made from multi-layer laminate materials with barriers against oxygen, light, and moisture. As the chips drop from the weigher into the forming tube, the film is pulled around the tube, sealed lengthwise, and sealed again at the top and bottom with heated jaws, creating a pillow-style bag. Before the top seal is made, a precise dose of nitrogen gas is injected into the bag, a process known as nitrogen flushing. This replaces the oxygen-rich air inside the package to reduce oxidation, extend shelf life, and protect the chips from crushing by slightly inflating the bag. Once sealed, each bag moves through a print station where batch codes, production time, plant ID, and expiration dates are applied using inkjet or thermal printers. Bags then pass through check weighers to confirm accuracy. Any bag outside the designated weight window is automatically rejected and diverted to a rework bin. Metal detectors or X-ray systems scan every bag to ensure no foreign objects have entered the product during processing. This is standard for all snack food production and a critical part of food safety compliance. From there, the sealed and verified bags are grouped into cartons or display trays by robotic case packers. These cartons are sealed with tape or glue and labeled with barcodes and tracking information. Finally, cartons are stacked onto pallets by robotic palletizers, often using suction cup grippers or clamp arms to gently stack without damaging contents. Pallets are wrapped in stretch film and staged in the finished goods warehouse, which is climate controlled to preserve chip texture and flavor. At every point along this packaging line, sensors, programmable logic controllers, and SCADA systems monitor performance metrics, line speed, reject rates, weigher accuracy, sealing temperature, film feed rate, and more. Maintenance logs and process trends are analyzed weekly to identify emerging issues, improve throughput, and reduce product loss. Beyond the physical movement of chips, there are strict sanitation and allergen management systems in place. Since some Ruffles flavors may contain milk, cheese, or other allergens, production lines must be deep cleaned between flavor runs. Clean in place protocols involve dismantling sections of the line using high-pressure washdowns, food-safe detergents, and microbial swab testing. Detailed records of every cleaning cycle are logged and audited regularly. In addition to cleaning, factories must manage cross-contamination risk during flavor changeovers. This includes running purge batches, segregating flavoring agents in separate storage silos, and using dedicated feed lines wherever possible. Every batch of Ruffles is linked back to a full traceability profile, covering raw material lot codes, equipment used, line operator IDs, and environmental conditions during processing. As the freshly packaged Ruffles chips leave the main production floor, the final phase of manufacturing comes into focus. A sophisticated web of logistics, sustainability efforts, continuous process optimization, and digital innovation. While the chips themselves are complete, the factory does not pause. Instead, a parallel system of data analysis, quality assurance, and supply chain orchestration continues operating in the background, ensuring the product not only meets current demand, but evolves to meet future expectations. These behind-the-scenes processes are integral to the long-term efficiency, environmental responsibility, and market success of Ruffles. At the heart of these operations is a factory-wide data infrastructure that tracks every input and output, from raw potatoes to finished pallets. Each batch of Ruffles produced is logged into an integrated manufacturing execution system. This software records the origin of each ingredient, the time and conditions of each processing step, the performance of every machine along the line, and even environmental metrics like room humidity and oil turnover frequency. The MES integrates with enterprise resource planning systems, providing real-time visibility into inventory levels, sales forecasts, and raw material consumption. This data is not merely archived, it's analyzed continuously using advanced analytics platforms and AI-based algorithms. These systems look for patterns in machine downtime, chip reject rates, oil consumption per batch, or seasonal fluctuations in potato solids. If a fryer begins to show a subtle increase in oil absorption, or if seasoning coverage becomes slightly more variable, the system flags it. Maintenance crews and process engineers receive alerts and can intervene before the issue affects product quality or efficiency. Predictive maintenance models also help avoid equipment failure by identifying when motors, pumps, or slicers are approaching wear thresholds. One of the key areas of focus in modern Ruffles factories is oil management. Frying oil is both a major cost and a major variable in product consistency and sustainability. The oil in the continuous fryer is constantly recirculated through filtration units that remove chip fines and particulates. Inline sensors monitor the free fatty acid content, color, and total polar materials in the oil, 3 indicators of oil degradation. When these metrics exceed defined limits, the system initiates partial or full oil replacement protocols. Some facilities have implemented smart fryer systems that dynamically adjust oil flow and heat profiles based on chip load and moisture level, significantly reducing oil turnover without compromising flavor or texture. Environmental sustainability is another priority embedded into Ruffles manufacturing. Frito-Lay, the parent brand, has committed to reducing water, energy, and greenhouse gas emissions across its snack food plants. One way this is achieved is through water reclamation. The flume water used to transport, wash, and rinse potatoes is filtered, UV treated, and reused multiple times before final disposal. Similarly, the steam peelers are equipped with condensate recovery systems that recycle steam condensate back into the boiler system, conserving energy and reducing water use. Electricity usage is optimized through variable frequency drives on conveyors and pumps, while LED lighting, motion sensors, and insulated cooling tunnels help minimize unnecessary energy waste. Some Ruffles production plants are now partially powered by renewable sources, including solar panels and biogas captured from on-site food waste digesters. Waste heat from fryers is recovered using heat exchangers and used to preheat incoming wash water, further boosting energy efficiency. Waste management is another crucial part of the factory's operations. Trimmings from biscuit cuts, chips rejected for size or overcooking, and seasoning overage are all collected, logged, and sent to animal feed processors or converted into biofuel when food safety protocols allow. Even the excess oil removed during de-oiling phases is collected, filtered, and sold to biodiesel manufacturers. Packaging materials are optimized for minimal plastic use, and packaging engineers continuously evaluate new laminates that offer better barrier performance with reduced environmental impact. The production of a Mars bar begins with the formulation and creation of its first major internal layer, the nougat. This nougat isn't the brittle kind you might find in traditional nut candies. Rather, it's a whipped, creamy, slightly chewy foundation that gives Mars bars their signature texture. Creating this nougat at industrial scale is a carefully engineered process that blends confectionery science with mass production machinery and strict environmental controls. Before the first batch of nougat is made, however, the ingredients themselves must be prepared and stored according to strict protocols. The base ingredients for the nougat are sugar, glucose syrup, water, fat typically palm or shea oil, dried milk powder, cocoa powder, and whipped egg white or egg albumin. All these materials arrive at the Mars manufacturing facility in bulk, delivered in tankers, tote bags, or sealed sacks. Each delivery is logged, barcoded, and entered into the site's inventory system. But before any ingredient enters production, it must pass Mars internal quality standards. All dry ingredients, such as sugar and milk powder, are transferred into enclosed silo systems using pneumatic conveyors. These silos are climate controlled and fitted with HEPA filtration to prevent contamination from dust or ambient air. Each ingredient batch is tagged with a barcode that traces it back to its supplier, production date, and previous storage conditions. For example, sugar may be tested for grain size, purity, and color using laser granulometry and ICUMSA color unit analysis. If it's outside tolerance, it's rejected immediately. Liquid ingredients like glucose syrup and oils are offloaded into jacketed stainless steel storage tanks through filtered, food-grade hoses. These tanks maintain the ingredients at set temperatures to ensure proper viscosity for pumping during production. Glucose syrup, for instance, is kept at around 40 degrees Celsius to remain fluid enough to move through piping without crystallizing. Oils are similarly heated and agitated to prevent separation or solidification. Once all components have been approved and staged, the first step in actual nougat production begins in a dedicated mixing chamber. This space is sealed off from other parts of the factory and maintained at specific humidity and temperature levels to preserve the quality and structure of the aerated product. Airborne particles are filtered through a multi-stage air filtration system, and stainless steel surfaces are sanitized before each production run. Nougat is made in large capacity continuous mixers, automated machines that blend ingredients while precisely managing flow rate, temperature, and mixing speed. In a traditional batch process, workers would mix sugar and glucose syrup with water and cook it to a specific temperature. But in Mars's high-speed factories, this process is carried out on a continuous flow basis, meaning raw ingredients are metered into the cooking system in real time, mixed, cooked, and then aerated in a constant stream. First, sugar, glucose syrup, and water are combined in a jacketed mixing vessel and brought up to temperature using indirect steam heating. The mixture must reach roughly 115 to 120 degrees Celsius, hot enough to dissolve all solids and achieve the correct consistency for whipping, but not so hot that caramelization occurs. Inline refractometers monitor the Brix level, sugar concentration, constantly, sending digital signals to a control system that adjusts syrup feed rate or cooking temperature as needed to stay within spec. Once the syrup reaches target temperature and concentration, it's transferred to a cooling chamber, where it's rapidly brought down to around 70 to 80 degrees Celsius using chilled water jackets. This temperature reduction is critical. It stabilizes the syrup mixture and prepares it for aeration with egg whites or albumin, which cannot be added while the base is too hot without denaturing the proteins. Now comes the aeration stage, where the characteristic lightness and chew of the nougat is created. A pre-prepared egg albumin solution is metered into the cooled sugar syrup in a continuous aerator. This machine functions much like a planetary mixer, but at vastly greater speed and scale. Blades spin at extremely high RPMs inside a sealed chamber, while air is injected under pressure. The result is a fluffy, stable foam that has the volume and consistency of whipped marshmallow. The air injected into the aerator is sterile and dry, supplied by an inline compressed air system equipped with microbial filters and dehumidifiers. Pressure, temperature, and air-to-liquid ratio are all controlled automatically via programmable logic controllers, PLCs, which adjust mixing speed and flow rate to maintain uniform aeration. If the density of the nougat mixture falls outside of target specifications, measured by inline densitometers, the system automatically corrects the air or syrup flow or alerts operators to intervene. At this point, cocoa powder and dried milk are added to the base. These ingredients give Mars Bar Nougat its unique color and rich malted taste. They are added using powder feeders that continuously meter the dry materials into the aerated mass as it exits the mixer. This blending occurs in a sealed paddle mixer with gentle, controlled agitation to avoid collapsing the foam structure. The resulting mixture is a warm, chocolatey nougat paste with a light, stable structure and a semi-elastic texture. Now that the nougat base is formed, it must be shaped and cooled. The nougat flows out of the mixer onto a stainless steel conveyor belt, forming a continuous slab about 2 to 3 centimeters thick. This slab passes through a chilling tunnel, where it is gradually cooled from around 60 degrees Celsius to just below ambient temperature. The tunnel uses recirculated cold air, zoned in multiple sections, to cool the nougat evenly without inducing condensation or hardening the outer surface too quickly. As the slab exits the chilling tunnel, it enters a cutting station. Rotary guillotine knives, synchronized with the belt speed, slice the slab crosswise into narrow ribbons, each of which will become the base layer of a Mars bar. These ribbons are then cut lengthwise by inline blades or ultrasonic cutters, creating rectangular nougat centers of uniform size. Every bar section is scanned by vision systems to check for dimensional consistency, length, width, and height, with auto-reject mechanisms removing any pieces that fall outside tolerance. The formed nougat segments are now ready to receive their second major component, the caramel layer. But before caramel is deposited, the nougat sections are spaced and aligned using lane diverters and product guides, ensuring that each bar proceeds uniformly through the next phase of production. The segments then pass into a buffer zone where their temperature is stabilized to prepare for caramel application. Now that the nougat segments are cooled, cut to precise dimensions, and cued in alignment on the conveyor system, the next phase in the Mars chocolate bar manufacturing process begins: the production and deposition of the caramel layer. This caramel is not a generic topping, it's one of the signature components that defines the textural and flavor contrast of a Mars bar. Creating this layer at scale requires a specialized process that integrates continuous cooking, emulsification, temperature control, and precision depositing, all engineered to work seamlessly within the speed and flow of a high-volume confectionery production line. The caramel used in Mars bars is made from a carefully balanced combination of sugar, glucose syrup, sweetened condensed milk or milk solids, and a specific blend of fats and emulsifiers. It's cooked to achieve a particular consistency, not too firm, not too runny, with a creamy chew that holds its shape during wrapping and storage, yet yields easily when bitten into. The production of caramel begins in a dedicated cooking area, separate from the nougat line, but synchronized with it to maintain constant throughput. All ingredients are stored in bulk near the cooking zone. Sugar and milk powders are gravity-fed from silos into high-shear premixes, while glucose syrup and fat are pumped in from temperature-controlled tanks. The emulsifiers, such as mono and diglycerides, are introduced through metering pumps in very small, tightly controlled amounts to help ensure smooth texture and fat water dispersion. A water phase may also be introduced at the start to aid in initial dissolution and prevent localized overheating. The entire mixture is first blended in a jacketed stainless steel preheating tank, where it's brought to a uniform temperature of around 70 to 80 degrees Celsius. This pre-cooking stage ensures that all ingredients are fully homogenized before entering the main caramel cooker. From here, the caramel mix is pumped continuously into a vacuum caramel cooker, a specialized machine that allows rapid, even heating while removing excess water to control the final solid's content and viscosity. Vacuum caramel cookers work by reducing the internal pressure in the cooking chamber so that water boils off at a lower temperature. This is crucial to avoid burning the sugars or overcooking the milk solids, which could lead to bitter notes or textural instability. Inside the cooker, the mix is heated to between 115 degrees Celsius and 120 degrees Celsius. The target is to achieve a final water content of around 6 to 8%, with a sugar concentration of roughly 80 to 85 brix. Inline refractometers monitor this constantly, and the cooker adjusts residence time or heating level as needed to meet the spec. Once cooked, the caramel exits the cooker as a thick, glossy liquid with a rich golden brown hue. But before it can be applied to the nougat, it must be slightly cooled and tempered to a very specific range, typically between 45 degrees Celsius and 55 degrees Celsius. This cooling step stabilizes the caramel structure, allowing it to flow evenly during deposition without dripping or bleeding into the nougat layer. Cooling is performed in a jacketed holding tank equipped with slow-speed agitators that prevent crusting and keep the mixture homogeneous. With the caramel at the correct temperature, it's piped toward the depositing station. Here, the aligned nougat segments are conveyed under a continuous curtain-style depositor or a series of timed nozzles. Each piece receives a uniform layer of caramel, typically around 5 to 6 millimeters thick, depending on the final product specification. The depositor is precisely synchronized with the line speed, often using servo motors and optical sensors, so that each caramel stream lands squarely on the nougat block without overflow or excess. In higher speed lines, a pre-formed caramel sheet may be used instead. In this method, caramel is spread onto a separate cooling belt, allowed to set into a thin slab, and then laminated onto the nougat in one continuous motion using compression rollers. This technique allows better layer thickness control at very high production speeds and ensures cleaner edges for slicing. Once the caramel is applied, the dual layer bar now enters another cooling tunnel, usually a multi-zone refrigerated belt system that brings the caramel from 50 degrees Celsius down to just under 20 degrees Celsius. This cooling step must be gradual and controlled. Too rapid, and the caramel may contract unevenly, leading to separation from the nougat. Too slow, and it may remain sticky, interfering with the next step. Chocolate enrobing. During cooling, the layered bar is gently compressed by a roller to ensure adhesion between nougat and caramel. Then, it's passed through edge trimmers, which shave off the sides of the slab to produce perfectly square bars with clean, vertical sides. These trimmed edges are not wasted. They are collected via vacuum conveyors and reprocessed, either remelted or reformed, depending on factory protocol. The bar, now comprised of a cooled nougat base and a bonded caramel layer, is next cut into individual pieces using high-speed guillotine cutters. These are precision machines equipped with hardened stainless steel blades or ultrasonic cutting systems that minimize drag and preserve edge integrity. Each piece is exactly the length and width of a finished Mars bar, around 10 centimeters long and weighing roughly 51 to 57 grams, depending on the market. As the bars are cut, they are spaced out evenly using puck conveyors or lane dividers, aligning them perfectly for entry into the chocolate enrobing section. The temperature, moisture, and dimensional uniformity of each bar are verified by inline sensors and vision systems. Bars that are cracked, too short, or unevenly shaped are automatically diverted off the line for manual inspection or rework. At this stage, we transition into the enrobing process, the iconic step where each bar is coated in a smooth layer of Mars' proprietary milk chocolate blend. This chocolate is stored in large tempering tanks, located just prior to the enrober. These tanks keep the chocolate at the ideal crystallization state, ensuring a glossy finish and firm snap after cooling. The chocolate used in Mars bars is a blend of cocoa liquor, cocoa butter, sugar, and milk solids, with added emulsifiers like soy lecithin to enhance flow properties. The tempered chocolate is pumped into the enrober, which is essentially a tunnel lined with a bottoming section to coat the base of each bar, and a curtain section to drape chocolate over the top and sides. Each Mars bar passes first over a shallow pool of chocolate to coat its underside, then directly beneath a flowing curtain that envelops the rest of the bar. A gentle stream of warm air is directed across the top to remove excess and create a rippled surface texture, a distinctive feature of the Mars bar. After enrobing, the bars are conveyed into the cooling tunnel, an extended refrigerated belt system approximately 20 to 30 meters in length. Inside, the environment is segmented into zones that gradually lower the temperature of the bars from around 32 degrees Celsius to 10 degrees Celsius. This staged cooling helps the cocoa butter in the chocolate crystallize properly, locking in the sheen and texture while avoiding fat bloom or streaks. Throughout this tunnel, air humidity is tightly controlled, generally under 50%, to prevent condensation on the chocolate. Dew point sensors and fans work in tandem with the refrigeration units to maintain a stable microclimate. The bars spend 5 to 8 minutes in this tunnel before emerging with fully set coatings, ready for packaging. As the cooled and finished bars exit the tunnel, they're fed into accumulation conveyors and grouped for wrapping. Each bar passes through a flow wrapping machine where printed film is unwound, formed into a sleeve, and sealed around the product. The wrapper is then crimp sealed on both ends and trimmed. These wrapping machines can process hundreds of bars per minute, and each wrapped bar is weighed and scanned before being discharged onto final packing belts. At this point, the product is visually indistinguishable from the Mars bar found on store shelves, but the process is still not finished. The next stage involves secondary packaging, grouping bars into boxes, cartons, and shipping trays, and preparing them for distribution. As the fully formed, enrobed, and cooled Mars bars make their way off the production line, they enter the final stages of the factory process, beginning with high-speed wrapping and continuing through automated boxing, palletization, storage, and outbound logistics. These downstream systems are critical not just for protection and presentation of the product, but also for ensuring traceability, quality retention, and supply chain synchronization. While the visible production, the mixing, cooking, cutting, and coating is complete, the final packaging and handling stages are no less intricate, built on robotics, data systems, and industrial automation designed to manage millions of units every day. The first stop is the wrapping station. Here, each Mars bar moves along the conveyor belt in single file toward the flow wrapping machine. This machine feeds a continuous roll of printed film into a series of folding arms and sealing jaws. As each bar enters, the film wraps around it in a tight, tubular sleeve, and heated crimp jaws at either end form the back seal and the end seals simultaneously. The temperature of these jaws is maintained within a few degrees of the sealing material's activation point to ensure strong, clean closures without melting or burning the film. Mars uses multi-layered packaging films that are designed not only to provide barrier protection against oxygen and moisture, but also to deliver the tactile feel and gloss that customers expect from premium chocolate packaging. The inner layer is typically a heat-sealable polymer. The middle layer may include aluminum or metallized PET for barrier properties. And the outer layer is printed with brand artwork and product information. The printed designs are registered with high-precision sensors, so every bar's logo aligns perfectly. Any misregistered wrapper is automatically detected and rejected by an optical scanner system. Once sealed, the wrapped bar passes over a check weigher, an in-motion scale that ensures the final packaged weight is within tolerance. If a bar is over or underweight, even by a gram, it's automatically diverted. Next, each unit is passed under a metal detector, which checks for any possible foreign objects that could have entered the bar during earlier processing stages. These systems are highly sensitive and calibrated daily with test pieces. Some plants also employ X-ray machines that detect not just metal, but dense, non-metallic contaminants, such as glass or stone. Bars that pass all inspections continue down the conveyor toward the cartoning line. Depending on the intended retail format, bars may be grouped into multi-packs, retail-ready trays, or shipping cartons. Robotic arms, or high-speed diverters, organize the flow of individual bars into stacks, 4, 6, 10, or 12 bars wide, and gently push them into pre-folded cardboard sleeves or boxes. These secondary packages are then sealed using hot melt glue or tuck-in flaps, depending on market requirements. Each package receives a printed label with batch number, timestamp, factory ID, and possibly a QR code for inventory tracking. From here, boxed products are routed to the palletizing station. Robotic palletizers pick up full cases using vacuum grippers or mechanical arms and stack them on wooden or plastic pallets in precise formations. Each layer is arranged to optimize space, balance, and load stability. Between layers, some systems add cardboard slips or corner protectors for reinforcement. Once the pallet reaches its programmed height, typically 1.6 to 1.8 meters, it's wrapped in stretch film by an automatic wrapper, which rotates the pallet while dispensing the film under tension to secure the load. The wrapped pallets are then fitted with pallet labels that include the SKU, total unit count, gross weight, destination code, and a unique identifier that ties back to the factory's internal tracking system. These labels are printed by thermal printers and verified by barcode scanners before the pallets are cleared to enter the finished goods warehouse. Before we go further, it's important to recognize the role of Mars factory control systems in managing this entire post-production phase. All equipment is integrated into a centralized manufacturing execution system, MES, that tracks every product in real time. Each bar, box, and pallet carries data, embedded in barcodes or RFID tags, about when it was made, on which line, using which ingredients, and under what conditions. This traceability is a cornerstone of food safety compliance and internal quality assurance. The finished goods warehouse is where the newly palletized bars await shipment. This warehouse is fully climate controlled to maintain optimal temperature and humidity for chocolate storage. Temperature is held at 18 to 20 degrees Celsius with relative humidity below 55% to prevent bloom, melting, or texture changes. Air circulation systems keep temperature consistent throughout the space, while insulation and vapor barriers prevent external fluctuations from impacting internal conditions. Inventory in the warehouse is managed using automated guided vehicles, AGVs, or forklifts equipped with real-time location systems. When pallets are stored, they're scanned into the warehouse management system and placed according to distribution priority. High turnover products are stored closer to the shipping bays, while seasonal or export variants may be stored deeper in the racking system. The storage time for any batch is typically less than a week, as Mars factories operate on just-in-time logistics, pushing product out daily to meet distributor orders. When shipments are requested, the warehouse team receives a digital pick list. AGVs or operators retrieve the designated pallets, verify them via handheld scanners, and stage them at the outbound docks. Before loading, each shipment is inspected to ensure it matches the order specification, is within temperature tolerance, and has intact pallet wrapping. Refrigerated or climate-controlled trucks are often used for long-distance shipments or deliveries to regions with high ambient temperatures. Loading is done using dock levelers and roller systems to ensure smooth movement and prevent tipping. During transit, temperature loggers accompany the shipments, recording data at set intervals. These loggers are checked upon delivery, and if any deviation from the acceptable range is detected, the shipment may be flagged for inspection or rejection. Mars also monitors customer feedback, market audits, and in-store quality surveys. Samples of each production lot are retained in climate-controlled storage at the factory for shelf life testing. These retained samples are periodically tested for appearance, taste, texture, and microbiological stability over the course of months, ensuring that every production protocol performs as expected long after the product has left the plant. Parallel to all of this is a dedicated quality control laboratory. Here, daily production samples are subjected to physical and chemical analysis. Moisture content, fat content, sugar crystallinity, pH, and emulsion stability are checked using instruments like Carl Fisher titrators, differential scanning calorimeters, and viscometers. Sensory panels trained in Mars' specific flavor and texture profiles evaluate samples for aroma, mouthfeel, and aftertaste. Auditors regularly conduct surprise inspections, testing product against regulatory standards in every region the factory exports to. Some facilities even run accelerated aging chambers, simulating 6 months of shelf life in a few weeks using controlled temperature and humidity cycling. This allows the company to predict how new packaging or ingredient changes may impact long-term stability before releasing them to the market. Within the final layers of Mars' chocolate bar manufacturing process lies an often unseen yet deeply critical infrastructure dedicated to innovation, iteration, and global standardization. While the production lines are optimized for high-speed consistency, behind the scenes, the company operates pilot plants and R&D laboratories, where new formulations, production methods, and equipment calibrations are continuously tested, refined, and validated before they're deployed across global facilities. Every Mars chocolate bar, regardless of where it is produced, in the United States, the United Kingdom, or other licensed manufacturing hubs, must adhere to an extremely narrow window of variation. This means the bars must look, taste, feel, and behave identically, despite being produced in plants thousands of kilometers apart. Achieving this demands extensive process documentation, real-time data comparison, and coordinated updates to recipes and equipment settings across all sites. Pilot plants, often located adjacent to main production facilities, house miniature versions of the full-scale equipment, scaled-down mixers, depositors, tempering tanks, and enrobers, used not just for prototyping new flavors or bar formats, but also for stress testing ingredient substitutions, adjusting for new cocoa sources, or modifying emulsifier levels in response to regional ingredient availability or regulation. A new Mars bar variant, such as one with an added layer of cookie or a salted caramel flavor, may go through dozens of test batches before scaling. Each trial is evaluated not just for consumer preference, but for how it performs on actual equipment. Does the caramel spread at the correct rate on moving belts? Does it maintain form through the cooling tunnel? Does the chocolate enrobe correctly without altering crystallization time? These questions are answered with data from test runs that are digitally logged and used to generate predictive models before any large-scale production begins. Digital twins, virtual simulations of real production environments, are increasingly being used in these trials. These tools model fluid dynamics, thermal behavior, and mechanical stress on ingredients during cooking, cooling, and transport. They allow engineers to simulate a dozen line changes without touching a single piece of physical equipment, drastically accelerating the pace of safe innovation. Once a new process is approved, Mars' global standardization team prepares comprehensive change packs, which include updated process parameters, safety protocols, ingredient specs, equipment calibration charts, and software updates. These packs are then distributed to all regional manufacturing hubs, often followed by remote training sessions or on-site visits to ensure implementation is seamless. This global coordination ensures that whether you open a Mars bar in Chicago, Sydney, or Madrid, the experience is identical, down to the snap of the chocolate, the elasticity of the caramel, and the melt rate of the nougat. Red Bull starts with its formula, a carefully guarded blend of ingredients that deliver its characteristic taste, texture, and functional effects. At the heart of the recipe is water, which serves as the main ingredient by volume. This water is not simply pumped from a municipal source and used directly. It undergoes multiple purification stages to ensure it is free of any dissolved solids, minerals, or microorganisms that might alter the taste or stability of the drink. The purification typically begins with coarse filtration to remove particulate matter, followed by activated carbon filtration to strip out organic compounds and chlorine, then reverse osmosis to achieve a very low mineral content. The final step often involves ultraviolet light treatment or ozonation to sterilize the water before it enters the production tanks. Once the water is ready, the remaining ingredients are prepared. These include sucrose and glucose for sweetness and energy, citric acid for acidity and flavor balance, taurine as a functional amino acid, caffeine as the stimulant, and B group vitamins like niacinamide pantothenic acid, vitamin B6, and vitamin B12. Each of these arrives at the factory in bulk form. Sugars as fine crystals, taurine and caffeine as purified powders, vitamins as either powders or highly concentrated solutions. All are stored under controlled conditions and tested in an in-house quality lab for purity and potency. The creation of the beverage begins with the preparation of a concentrated syrup. In large stainless steel blending vessels, precise amounts of sugar are dissolved in purified water under gentle heat, usually between 50 and 60 degrees Celsius, to speed dissolution without caramelizing the sugar. The glucose syrup, if used in liquid form, is pumped directly into the blending vessel through sanitary pipelines. Once the sugars are fully dissolved, the other functional ingredients, taurine, caffeine, and vitamins, are added in carefully measured doses. This mixing process is critical. Operators rely on automated ingredient dosing systems connected to load cells and flow meters to ensure exact quantities, as even a small deviation could alter flavor or regulatory compliance. Citric acid is then introduced to adjust the pH, giving Red Bull its slightly tart backbone and enhancing stability. Flavors, which are part of a proprietary blend, are also incorporated at this stage. These may include natural and artificial components that together create the drink's distinctive aroma and taste. The mixing tanks are fitted with high-speed agitators to ensure uniform distribution of all ingredients, and the resulting syrup is tested in the lab for Brix, acidity, and flavor profile before moving forward. Once the base syrup is complete, it is diluted with more purified water to bring it to the target concentration for the finished beverage. This final liquid mixture, now containing all flavor and functional components, is chilled to prepare it for carbonation. Carbonation is one of the defining aspects of Red Bull's sensory experience, and it is performed with great precision. The chilled beverage passes through a carbonator where it is brought into contact with carbon dioxide under high pressure. The CO2 dissolves into the liquid with the level carefully controlled. Too little carbonation would make the drink taste flat, while too much could affect mouthfeel or cause excessive foaming during filling. The carbonated beverage is then immediately directed to the filling lines. Red Bull is packaged almost exclusively in aluminum cans, chosen for their lightweight nature, excellent barrier properties against light and oxygen, and recyclability. These cans arrive at the factory in massive stacks of unprinted or pre-printed containers, each one spotless and free from dents or imperfections. Before filling, they undergo a thorough rinse with deionized water or ionized air to remove any dust or debris. The rinsed cans move down the line on high-speed conveyors into the filling carousels. The filling process operates at incredible speed, often hundreds of cans per minute, and is performed in a pressurized environment to maintain carbonation. Each can is filled from the bottom up to minimize turbulence and foaming, then immediately sealed with an aluminum end by a seaming machine. This seam is a precision crimping of the lid to the can body, creating an airtight and watertight seal. Once sealed, each can is inverted briefly to ensure the lid is fully sanitized by contact with the beverage inside, then returned upright. Immediately after sealing, cans pass through automated inspection systems. These use a combination of cameras, sensors, and weight checks to identify any underfilled, overfilled, or defective cans. Any can that fails inspection is automatically rejected and diverted from the main conveyor. Approved cans move on to pasteurization or cold sterilization, depending on the plant's process design. Pasteurization involves heating the cans to a specific temperature for a set time to ensure microbial stability, while cold sterilization uses aseptic filling combined with sterilized containers to achieve the same result without heat. Once the cans are confirmed safe and stable, they head to the secondary packaging area. Here, they are grouped into the familiar 4-packs, 6-packs, or larger cases using cardboard wrap or shrink film. Automated cartoners or shrink wrappers handle this at high speed, often in combination with robotic case packers that load the multi-packs into corrugated shipping cases. The shipping cases are sealed with tape or hot melt glue, coated with batch information for traceability, and then stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability and transported to a climate-controlled warehouse. Although Red Bull is shelf-stable at room temperature, storage away from excessive heat or direct sunlight helps maintain carbonation and flavor over time. From the warehouse, pallets are loaded onto trucks bound for distribution centers and retailers. Given Red Bull's global reach, many of these pallets also enter intermodal shipping containers for transport by rail or sea to other countries. Throughout production, the emphasis on quality and consistency is relentless. Every batch of syrup and finished beverage undergoes analytical testing to confirm caffeine content, vitamin levels, acidity, and carbonation. Sensory panels taste samples to ensure the flavor matches the established profile. On top of that, microbiological testing verifies that no harmful organisms are present, and shelf life trials confirm that the product will remain stable through its intended storage period. The machinery in a Red Bull plant is highly automated, reducing human contact with the product to a minimum. Operators oversee systems via control rooms equipped with touchscreens that display real-time data on mixing temperatures, carbonation levels, filler speeds, and line efficiency. Maintenance crews work behind the scenes to keep pumps, compressors, and conveyors in top condition, as any downtime on a high-speed beverage line can be costly. Sustainability is also a growing focus in Red Bull production. Aluminum cans are already among the most recyclable packaging formats, and many plants source cans with a high percentage of recycled content. Water purification systems are designed to minimize waste, and heat recovery from pasteurization can be used to preheat water for syrup preparation. Efficient compressors and motors reduce energy consumption, and many facilities work to optimize transport logistics to cut fuel use in distribution. What makes the Red Bull process particularly interesting is how tightly controlled and repeatable it must be. The drink's formula is identical worldwide, which means a can produced in Austria should taste exactly the same as one produced in the United States or Asia. Achieving this level of uniformity across multiple plants requires not only identical recipes and ingredients, but also standardized equipment, operating procedures, and quality control protocols. Every plant is essentially a mirror of the others, ensuring that no matter where it's made, Red Bull delivers the same signature flavor, carbonation, and energizing effect. Every can of Monster begins with its ingredients, and the largest component is water. The water used in Monster Energy production is not simply drawn from a tap, it is subjected to a thorough purification process to remove any dissolved solids, organic compounds, or microorganisms that could affect taste, appearance, or stability. The typical sequence starts with coarse filtration to catch sediment, followed by activated carbon filters to strip out chlorine and odors. Reverse osmosis membranes then reduce mineral content to near zero, creating a blank canvas for the flavor formulation. As a final step, ultraviolet light or ozone is used to sterilize the water before it enters the mixing tanks. Next come the sweeteners, functional additives, acids, and flavors that give Monster its distinctive taste and energy-boosting profile. Cane sugar or beet sugar may be used along with glucose or high fructose corn syrup, depending on the variant and market. These sugars arrive in bulk either as crystalline solids or liquid syrup in tanker trucks. Functional ingredients include caffeine for stimulation, taurine as an amino acid additive, and B vitamins like niacin, riboflavin, vitamin B6, and vitamin B12 to support energy metabolism. Some varieties incorporate plant extracts such as ginseng or guarana, which add both flavor and functional appeal. Acids like citric and sometimes malic acid adjust the pH for tanginess and preservation, while natural and artificial flavors create the unique profile for each Monster variety, from the classic green logo flavor to tropical, coffee-based, and sugar-free blends. The first main step in production is the preparation of the concentrate or syrup. In large stainless steel mixing vessels, sugar is dissolved into heated purified water under gentle agitation. If liquid sweeteners are used, they are pumped directly in and blended. Functional powders like caffeine and taurine are carefully weighed and added in controlled sequences to ensure complete dissolution without clumping. B vitamins, which are sensitive to heat, are typically added later in the process to preserve potency. The plant extracts, if used, are measured and incorporated at specific points, often emulsified to ensure they disperse evenly throughout the drink. Flavor concentrates, which can be highly potent, are metered into the mix using precision dosing pumps. These concentrates often contain a mixture of flavor oils, sweeteners, and acids in a stable base that integrates easily into the water-sugar matrix. Because Monster produces a wide variety of flavors, the plant must be capable of switching from one concentrate to another with minimal downtime. A challenge that requires clean-in-place systems to flush and sanitize mixing tanks and pipelines between batches. Once the syrup is fully blended, it is tested in the quality control lab for sweetness, acidity, caffeine content, and flavor profile. The lab team uses sensory analysis alongside instrumental testing to ensure the mixture matches the established standard. Only when it passes these checks is it moved forward. The next stage is dilution and carbonation. The concentrated syrup is blended with additional purified water in large batch tanks to reach the target formulation for the finished drink. This diluted beverage is chilled to near freezing temperatures to maximize the solubility of carbon dioxide during carbonation. The chilled liquid enters a carbonator, where CO2 is injected under high pressure and mixed through fine diffusers or inline mixers. The carbonation level is closely controlled. Too little, and the drink will taste flat. Too much, and it will foam excessively during filling. Once carbonated, the beverage moves immediately to the filling lines. Monster Energy is almost always packaged in aluminum cans, chosen for their lightweight, barrier properties, and recyclability. These cans arrive at the plant in massive pallets of unfilled containers, often printed with Monster's signature claw mark logo and variant-specific graphics. Before filling, each can is inverted and passed through a rinser, which uses either deionized water or ionized air to remove any dust or particles. The cans travel into high-speed rotary filling machines where they are filled from the bottom up to reduce foaming and preserve carbonation. Each filler head dispenses an exact volume, ensuring every can meets legal net content requirements. Immediately after filling, the cans pass into a seaming machine, where an aluminum lid is placed on top and mechanically rolled into place to form a double seam that locks the contents in airtight. This seaming process is a critical control point. Improperly sealed cans can lose carbonation or leak, so seamer performance is constantly monitored. Sealed cans are inverted briefly so that the liquid inside can contact the underside of the lid, which acts as a quick sterilization step. Depending on the plant's process, the cans may then undergo tunnel pasteurization. Moving through a heated water spray tunnel that raises the beverage temperature for a specific time to kill any microorganisms. Or may rely on aseptic filling techniques that eliminate the need for heat treatment. Once pasteurized or otherwise stabilized, the cans are cooled rapidly to prevent heat damage to vitamins and flavors. They then pass through a series of inspection systems. Automated vision cameras check for dents, damaged seams, or incorrect graphics. Check weighers ensure that each can contains the correct amount of product, and any deviation triggers an automatic rejection. Many lines also incorporate inline gas analysis to confirm carbonation levels in the finished product. The approved cans move into the secondary packaging area, where they are grouped into multi-packs. This may involve cardboard carriers, shrink-wrapped bundles, or trays depending on the market. Automated packers arrange the cans in the correct pattern, wrap or enclose them, and send them toward the case packing stage. Here, multi-packs are loaded into corrugated shipping cartons, which are sealed, coated with batch and date information, and stacked by robotic palletizers. Pallets are wrapped in stretch film to secure the load and sent to the warehouse for storage. Even though Monster Energy is shelf-stable at room temperature, it is generally stored in cool, dry conditions to maintain flavor and carbonation quality. From the warehouse, products move through distribution networks to retail shelves worldwide. Behind all of these steps is a rigorous quality control program. The production team pulls samples at every stage: syrup preparation, dilution, carbonation, filling, and post-packaging to confirm compliance with product specifications. Analytical labs test for caffeine content, sugar level, vitamin potency, pH, and carbonation. Microbiological testing ensures that no spoilage organisms are present. Sensory panels evaluate taste, aroma, and mouthfeel to maintain brand consistency. The machinery that makes this possible is heavily automated. Operators work from control panels in climate-controlled rooms, monitoring temperatures, pressures, flow rates, and carbonation levels via touchscreen interfaces. Programmable logic controllers coordinate the entire process, from mixing through palletizing, and sensors throughout the plant send real-time feedback. This automation allows Monster to produce enormous volumes with minimal downtime, while meeting strict safety and quality standards. Sustainability considerations are increasingly built into Monster's operations. Aluminum cans are highly recyclable, and many suppliers provide them with a significant proportion of recycled content. Water purification systems are designed to recover and reuse as much water as possible in non-product applications like cooling or cleaning. Heat from pasteurization is often recovered and used to preheat water for syrup preparation, reducing energy demands. Transportation logistics are optimized to reduce emissions, and some plants have moved towards renewable energy sources for part of their power. What is most striking about Monster Energy production is its consistency. The brand's image may be chaotic and wild, but the drink inside is the product of careful, repeatable processes that leave nothing to chance. Every step is measured, every variable tracked, every can inspected, ensuring that when a consumer pops the tab and hears that sharp hiss of carbonation, they get exactly the flavor, mouthfeel, and energy hit they expect, whether they bought it in a gas station in California or a convenience store in Seoul. The making of a can of Celsius Energy is a study in a modern beverage manufacturing where health-focused marketing meets industrial-scale precision. Although the drink is promoted as a fitness or metabolism-boosting energy beverage, the underlying production process is much like that of other carbonated functional drinks. A carefully balanced formula of water, sweeteners, active ingredients, and flavors blended, carbonated, and packaged under conditions designed to maintain purity, consistency, and shelf stability across millions of units. It begins with the most abundant ingredient, water. Water quality is paramount in Celsius production because any dissolved minerals, organic matter, or off flavors could interfere with the delicate flavor balance and the stability of the added functional ingredients. Purification is achieved through a series of treatments. First, the incoming water is screened through coarse filters to remove particles. Activated carbon filters then strip out chlorine, residual odors, and organic compounds. Reverse osmosis membranes reduce dissolved solids to extremely low levels, creating a neutral base. Finally, ultraviolet light or ozonation is applied to sterilize the water before it enters the formulation tanks. Once the water supply is ready, the functional and flavor ingredients that distinguish Celsius are prepared. Unlike traditional energy drinks that lean heavily on sugar and caffeine alone, Celsius incorporates a blend of caffeine from both synthetic and natural sources, such as green tea extract and guarana seed extract. It also features taurine, B vitamins, vitamin C, and in many varieties, additional plant extracts such as ginger root extract for a warming, metabolism-supporting effect. Some variants are sweetened with cane sugar, while many zero sugar options use non-nutritive sweeteners like sucralose or stevia extract. Acids like citric acid and malic acid are used to balance the flavor profile and help preserve freshness, while natural flavors, often fruit-based, create the distinct taste of each variety, from sparkling orange to peach vibe. The first major step in production is creating the base concentrate or syrup. This happens in large stainless steel mixing vessels equipped with high shear agitators or propeller mixers to ensure complete dispersion of both solids and liquids. For sugar-containing variants, crystalline sugar is metered into the purified water and dissolved at a controlled temperature to speed up the process without causing caramelization. If the formula calls for 0-calorie sweeteners, these are introduced in microgram precise quantities via automated dosing systems, as their sweetness intensity is many times greater than that of sugar. Functional powders such as caffeine, taurine, and vitamin C are weighed with laboratory-grade scales before being added. Plant extracts often arrive as liquid concentrates or fine powders and may require pre-dissolution in a small amount of water or glycerin to ensure they blend smoothly without clumping. For heat-sensitive ingredients like vitamin C, addition occurs towards the end of mixing to minimize degradation. Throughout this stage, the pH is monitored and adjusted as needed, since certain active compounds are more stable within specific acidity ranges. Once all solids are dissolved and liquids are homogenized, flavoring compounds are introduced. These may be natural fruit essences, essential oils, or compounded flavors from specialist suppliers. The flavoring process is highly sensitive. Even slight, over, or underdosing can shift the sensory profile away from the established standard. The completed syrup is sampled and sent to the in-house quality control laboratory for analysis. There, technicians measure sugar concentration, acidity, caffeine content, and other activities, and conduct sensory evaluations to confirm taste matches the reference profile. After passing these checks, the syrup is diluted with more purified water to the final formulation strength in large batch tanks. At this stage, the beverage is chilled to near freezing temperatures in preparation for carbonation. Carbonation is one of the signature sensory features of Celsius's sparkling varieties, and it is carried out with precise control over dissolved CO2 content. The chilled liquid flows into a carbonation unit where carbon dioxide gas is injected under pressure, dissolving evenly into the liquid. The goal is to achieve a crisp, sparkling mouthfeel without excessive foam that could cause filling issues. From the carbonator, the beverage is pumped directly to the filling lines. Celsius is typically packaged in slim aluminum cans, often the 12-ounce or 355 milliliter size, chosen for their portability, shelf life stability, and recyclability. The empty cans arrive at the plant in palletized stacks and are fed onto conveyors. Before filling, they undergo a rinse using ionized air or deionized water to remove any dust or particles. The cleaned cans are inverted, then righted, and sent into the filling carousel. The filling process operates at high speed, often hundreds of cans per minute, and is done under conditions that protect carbonation. Each filler head dispenses an exact volume from the bottom up to reduce turbulence. Immediately after filling, the cans move into a seaming machine, where an aluminum lid is placed on each and mechanically crimped to form an airtight seal. This seam is a critical element of the can's integrity, and seaming stations are regularly checked with seam micrometers to verify proper formation. Sealed cans may pass through a pasteurization tunnel, depending on the plant's preferred stability method. In pasteurization, the cans travel along a conveyor under sprays of hot water that raise the internal beverage temperature to a specific target for a defined time, killing any potential microorganisms. Afterward, the cans are cooled quickly to protect heat-sensitive nutrients. In some plants, aseptic filling technology is used instead, allowing the drink to be filled into sterilized cans without the need for post-fill heat treatment, which can better preserve delicate flavors and vitamins. Once cooled, the cans pass through a series of inspection systems. Vision systems scan for dents, label defects, or improper graphics. Check weighers ensure the net content is correct, and any can outside the tolerance is automatically rejected. Inline gas analyzers may measure CO2 content to confirm carbonation consistency. Approved cans enter the secondary packaging stage, where they are grouped into multi-can packs. Cardboard sleeves, shrink film, or tray packs are applied depending on the distribution plan. Multi-packs are collated into corrugated shipping cases, which are sealed with glue or tape and printed with batch codes for traceability. Robotic palletizers stack these cases onto pallets in stable patterns, after which the pallets are wrapped in stretch film to secure them for transport. The finished pallets move into climate-controlled warehouse storage. Celsius products are shelf-stable, but temperature control helps maintain flavor, carbonation, and nutrient stability over the shelf life. From here, pallets are shipped to distributors, retailers, and online fulfillment centers worldwide. Throughout this process, quality control is constant. Samples from each batch are tested for caffeine level, vitamin potency, flavor accuracy, pH, and carbonation before release. Microbiological tests ensure no spoilage organisms are present. Sensory panels evaluate the finished drink for mouthfeel, aftertaste, and aroma, comparing it to the brand standard. Because Celsius positions itself in the better-for-you beverage category, consistency in active ingredient content is especially critical, and certificates of analysis often accompany each production run. Behind the scenes, this is all enabled by a network of highly automated equipment controlled by programmable logic controllers. Operators monitor the process from control stations, adjusting parameters like mixing speed, carbonation pressure, or filler settings as needed. The plant's clean-in-place systems allow tanks, pipelines, and fillers to be washed and sanitized automatically between batches, ensuring hygiene without extended downtime. Sustainability is an increasing focus in Celsius production. Aluminum cans are infinitely recyclable, and many suppliers now provide cans with a high percentage of recycled content. Plants work to reduce water use in cleaning and cooling, recover heat from pasteurization to preheat processed water, and optimize transport routes to cut emissions. Some facilities integrate renewable energy into their operations, such as solar panels or purchase agreements for green electricity. What makes the Celsius production process interesting is the careful balance between functional beverage science and mass-market beverage engineering. While the plant extracts and nutrient additions require precise handling to maintain potency and stability, the large-scale manufacturing environment demands speed and efficiency. The result is a beverage that can deliver consistent taste, carbonation, and nutritional content across millions of cans, while supporting the brand's positioning as a lifestyle-oriented, health-conscious energy drink. The journey begins with picking the perfect potatoes. But not just any potatoes will do. McDonald's chooses only russet Burbank potatoes for their fries. These aren't your average spuds. They're chosen for their unique qualities, making them perfect for frying. These potatoes aren't picked just because they taste good. They're also chosen because they can keep the proper quality and texture even when made in big batches for fast food. Take the United States, for instance, where russet Burbank potatoes are a top pick, and most McDonald's contractors are from the US. Here, you can see how the potatoes are dug up from the ground with the help of heavy-duty, all-in-one machines. Inside these machines, advanced tools clean the potatoes, removing all the dirt. This process continues until all the potatoes are gathered. All these potatoes are then collected and stored in a room. This way, they can be quickly taken out when needed, ensuring that the processing never stops. You'd be amazed by the sheer quantity of potatoes here. Believe it or not a single potato goes bad. They're all used up within 15 days. A big reason for this is that McDonald's makes approximately 9 million pounds of French fries every day. As soon as these potatoes are taken to the factory as needed, that's when the real magic begins. Let's take you inside the factory, where you'll see French fries being made. First up, we've reached the potato washing station. Here, the potatoes are tossed into cleaning containers filled with water. Thanks to vibrating belts, the fast-flowing water easily washes away the dirt from the potatoes. After a thorough wash, a portion control elevator lifts the potatoes out of the water and transfers them to another belt. This belt gradually collects the potatoes in a container-like hose, sending small batches to the peeling machines for further washing. The peeling process is incredibly delicate, ensuring only the skin is removed without wasting any part of the potato. Once the potatoes are peeled and clean, they're moved through belts to the third washing chamber. Here, the final wash takes place with water containing chlorine and safe chemicals. Freshly washed and ready, these potatoes are then taken by the belts for special treatments. What you're seeing, all these units standing tall, are actually fine cutting chambers. They expertly cut the peeled potatoes into uniform sizes. This is why McDonald's fries always look the same in shape and length. Their machines work in a precise and effective way. The machines propel the potatoes at speeds of 60 to 70 mph through high-pressure water knives. These water knives finely slice the potatoes into thin strips, which are then sorted by their size and shape. After being cut, the fries are washed again and then placed on an automatic elevator, taking them toward the boiler for the next step in their journey to becoming perfect fries. Sometimes the cut fries get special treatment with a mix of sugar and sodium acid pyrophosphate for two main reasons. The sugar helps the fries achieve that perfect golden brown color when fried, while the sodium acid pyrophosphate keeps the fries from turning grey or brown, whether they're cooked or frozen. The real reason they're boiled for a bit is to make the inside of the fries soft, so when they're fried later, they turn out crispy on the outside but remain soft inside. The fries head straight to the boiler. Here, any broken or misshapen fries stick to the belts, while the perfectly shaped fries fall through to the boiling area. They're fried to 50% to lock in the quality, flavor, and freshness from the inside out. This step also removes some water and starch from the fries, creating a light crust on them. The oil they're fried in is a mix of canola, corn, soybean, and hydrogenated soybean oils. This blend is healthy because it doesn't contain trans fats or cholesterol. After the fries are half fried, they're taken out with an elevator and set aside to air dry. This usually takes about 5 to 10 minutes. During this time, any extra oil dries up, making the crispy, half-cooked fries ready for packing. The fries that are only half-cooked get frozen super fast in a special freezer tunnel. This keeps their taste and texture just right. Freezing them quickly is important to make sure they all look the same and can be stored without going bad. Potatoes can spoil quickly once they're peeled or cooked. After that, the fries are put in cool trucks or storage areas, all set to be sent off to restaurants. Cutting onions seems like the toughest part of cooking, right? It's the reason half of us are scared to even start cooking. But what if we told you that you could skip that mountainous task entirely? These machines are so efficient that no matter how you place the onion, they'll figure it out, set it right, and then, with the help of a belt that looks like a bunch of molds, make peeling and cutting super easy. First, gadgets that remove the tough outer layer grab onto the onion and peel it away in no time. Look at how cleanly and perfectly peeled these onions are now, all thanks to these fantastic machines. After a manual quality check to ensure no bad onions slip through, they're sent to be cut. This manual check is crucial. If there's a bad one, it can be caught and removed by hand. With incredibly precise cutting, all these onions are then packed and frozen, ready to help you out in the kitchen. If you want to get the job done without even touching the fish, don't worry, these machines will do everything for you. You won't have to touch them at all. These preset units seal a specific amount of fish into packets perfectly. It's rare for these machines to make mistakes. Well, to say they never do would be stretching it. They do make errors, but only at a rate of 0.001%, because they're tested over 100 times before being used in factories. First off, thanks to their excellent eyesight, these machines quickly sort out the bad apples to one side while the good apples gently move along the belt. These good apples are on their way to be turned into apple puree, which is used in a variety of delicious dishes. These machines process a ton of apples into smooth, sweet puree in no time. It's amazing to see apples zip through this process and come out as something that makes our food taste so good. The apple skins are removed and sent to another area, often ending up mixed into fodder at dairy farms. Here we have one of the biggest and most famous automated lines for making pancakes. You'll see everything from the batter being poured to the pancakes being cooked and layered, all done by machines without a hitch. These molds take a ride through an oven where the pancakes are cooked until they're just right, golden and delicious. After cooking, the pancakes are carefully picked up and arranged into neat stacks, ready to be packed and shipped out. On vast plantations near the equator, coffee trees grow in neat, endless rows that sway in warm winds, their leaves glossy under the sun. The air smells faintly of earth and sweetness, and the red coffee cherries glint among the green like hidden jewels. Inside each cherry are 2 seeds, the coffee beans themselves. And it's these tiny seeds that will eventually be transformed into the brown, aromatic crystals that dissolve instantly in hot water. Harvesting is the first decisive step, and it's not as simple as it might seem. The timing has to be perfect. If the cherries are picked too early, the beans inside will be grassy and acidic. Too late, and they'll be dull or fermented. Some farms rely on hand picking, where skilled workers move along the rows and pluck only the ripest cherries, their baskets filling slowly over the day. Others use machines that shake the trees just enough to loosen mature fruit while leaving the rest intact. Once collected, the cherries begin to ferment almost immediately, so they must be processed within hours, washed, pulped, and spread out to dry under the open sky, or in mechanical dryers that blow warm air across the beans until their moisture drops to about 12%. At this stage, the beans are pale green, hard, and far from aromatic. They smell grassy, not roasted, and they're still covered in a thin, papery skin called parchment. Once removed, the beans are graded and sorted. Optical sensors check for color consistency, while air jets remove lighter impurities like husk or dust. It's astonishing how much attention is paid before the real transformation even begins. The coffee destined for instant products usually comes from Robusta or blended varieties, chosen for their strong flavor and high caffeine content, though some factories mix in Arabica for a smoother profile. These raw beans are then shipped in enormous containers to processing plants. When they arrive, they enter a world of polished steel, heat, and carefully timed automation. The first major operation is roasting, and this is where the green beans become the coffee we recognize. In a factory, roasting isn't done in small drums, like at an artisan cafe. Instead, it happens in vast, continuous roasters that can handle hundreds of kilograms per cycle. Inside these machines, hot air circulates at temperatures between 200 and 250 degrees Celsius, gently turning the beans as they darken and expand. During roasting, hundreds of chemical reactions take place: caramelization of sugars, breakdown of acids, and the famous Maillard reaction, which produces the deep, brown color and the complex aroma. The beans crack audibly as internal moisture and gases expand, a sound like faint popcorn popping. The air fills with a rich, smoky smell that's both bitter and sweet, carrying notes of chocolate, toasted nuts, and spice. Sensors monitor every variable, temperature, humidity, even the reflectivity of the beans, to ensure perfect uniformity. Too light a roast, and the flavor will be thin. Too dark, and it turns harsh. When the beans reach their target profile, they're cooled almost instantly with powerful air jets. This sudden cooling, called quenching, halts the roasting process immediately. Without it, the residual heat would continue cooking the beans, distorting their flavor. The freshly roasted beans emerge warm to the touch, oily and intensely aromatic. Standing near a cooling tray in such a plant is unforgettable. The smell alone could fill an entire warehouse. Next comes grinding. The roasted beans are brittle now, and they're fed into industrial grinders that crush them to a carefully controlled particle size. The grind is crucial. Too fine, and extraction becomes muddy and overdone. Too coarse, and the coffee loses strength. Factories use multiple stages of grinding, passing the coffee through rollers that steadily reduce it to uniform granules. The goal isn't to make powder yet, but to prepare it for extraction, the step that essentially brews the coffee on an enormous scale. Extraction takes place in tall, stainless steel columns that can rise several stories high. Imagine a giant version of a French press operating under precise heat and pressure. Hot water, usually around 150 to 180 degrees Celsius, is pumped through the columns under pressure, allowing it to extract soluble compounds from the coffee quickly and efficiently. The process happens in stages. The first columns capture delicate aromas and acids. The later ones draw out stronger, more bitter flavors and solids. Technicians monitor the strength of the extract as it flows through, adjusting the ratio of stages to achieve a balanced, full-bodied flavor. What comes out at the end of this step isn't a drinkable beverage. It's a thick, dark syrup, many times more concentrated than brewed coffee. It looks almost like molasses and smells intensely roasted. The challenge now is to turn that syrup into something solid, something that can dissolve back into liquid form later without losing the original aroma or taste. Before drying, the extract is filtered to remove insoluble particles and oils that could cause clumping or uneven texture. Some factories even distill the coffee vapors released during extraction, capturing volatile aromatic compounds that might otherwise be lost. These are stored separately and later reintroduced to the powder to enhance flavor. Every fraction of aroma matters. The goal is to retain as much of the fresh brewed character as possible. Now comes one of the most fascinating parts of the entire process: drying the extract into powder. There are two main methods used in the industry: spray drying and freeze drying, each producing a distinct kind of instant coffee crystal. Spray drying is the faster, more economical option. The coffee extract is sprayed through fine nozzles into a towering chamber filled with hot air. The droplets, suspended mid-air, dry almost instantly as they fall, turning into tiny hollow spheres of coffee powder before they even reach the bottom. The air smells warm and toasted, and inside the chamber, it looks like a golden brown mist of particles drifting down in slow motion. By the time the powder hits the collection floor, it's completely dry, light, crisp, and ready to dissolve in water. The temperature must be carefully controlled to avoid burning the powder or driving off too much aroma. Some factories re-inject the previously captured aromatic compounds at this stage, gently coating the powder as it cools, giving it that fresh coffee scent when the jar is opened. Freeze drying, on the other hand, is slower and more delicate, often reserved for premium instant coffees. In this method, the extract is first cooled into a slushy concentrate and then frozen solid at extremely low temperatures. The frozen slabs are broken into small pieces and placed in vacuum chambers, where the ice is removed through sublimation. It turns directly from solid to vapor without melting. What's left behind is a porous, crystalline structure that preserves both flavor and aroma remarkably well. These crystals have a satisfying texture and a rich color, and they dissolve beautifully in hot water, recreating a more authentic coffee experience. Both methods require immense energy and precision. The machinery involved looks like something out of a chemical plant. Huge dryers, insulated vacuum vessels, intricate networks of pipes and valves. The roar of air compressors and the hum of pumps fill the background constantly. Despite the industrial scale, every step is about preserving the soul of the coffee bean, the delicate aromatic balance that defines the beverage. Once the drying is complete and the coffee has taken on its familiar granular form, the next stage focuses on perfecting its texture and appearance. Because raw dried coffee powder, whether spray dried or freeze dried, can sometimes be too fine or irregular, leading to clumping, uneven dissolving, or a dusty appearance that doesn't feel right when poured into a cup. To solve this, factories use a process called agglomeration, a word that sounds technical but describes something quite intuitive. It's the gentle binding together of the fine particles into slightly larger, more uniform granules, each with a porous structure that allows water to rush in and dissolve them instantly. In a large stainless steel chamber that hums with quiet, steady vibration, the fine coffee powder is sprayed once again with a controlled mist of steam or warm water. The moisture causes the tiny particles to stick together just enough to form clusters, which then tumble in a rotating drum. As they move, warm air circulates around them, drying the clusters once more and locking them into place. The result is a grain that looks a bit like brown sugar. Irregular, yet cohesive, sturdy enough to resist dusting, but still fragile enough to melt away the instant it meets hot water. Workers and sensors constantly monitor the particle size and density because both affect not just how the coffee dissolves, but how it looks and feels when it hits the spoon. A slightly darker hue or a subtle sheen can change consumer perception entirely, so the factory's control room pays close attention to every detail. Once the texture is perfected, the granules are cooled and transferred through sealed pipes towards the packaging lines. At this point, the air in the plant is thick with roasted aroma. Even from a distance, it smells like an enormous cafe. The coffee, however, is vulnerable. Those delicate aromatic molecules that give it depth can easily evaporate or be degraded by exposure to oxygen or moisture. To preserve them, factories maintain strict environmental controls. The rooms are cool, dry, and filled with filtered air. Humidity levels are tightly regulated. In some sections, nitrogen is pumped into the air system to push out oxygen altogether, creating an inert atmosphere that keeps the product fresh. Before packaging begins, samples are taken from every batch and sent to the quality control lab. There, technicians test the granules for moisture content, solubility rate, color uniformity, and flavor intensity. Small brews are made using carefully measured water at specific temperatures, and trained tasters evaluate aroma, body, and aftertaste. Instant coffee might appear simple, but each brand has a signature profile that must be reproduced consistently. That warm nuttiness, that faint hint of chocolate, that gentle bitterness that feels coffee-like without being overwhelming. Consistency is everything, and even a minor variation in roast or extraction can shift the flavor away from the standard. When the batch is approved, it moves along a system of conveyor belts that lead to the filling machines. These machines are wonders of precision engineering. Tall, multi-nozzle dispensers that can fill hundreds of jars or sachets per minute without spilling a single grain. Glass jars, plastic containers, or foil pouches arrive from another line, cleaned and sterilized with blasts of filtered air or ultraviolet light. The filling system measures exact weights with digital accuracy, sometimes adjusting in real time as sensors detect minute fluctuations in density. The gentle hiss of nitrogen fills the headspace of each container before sealing, a protective cushion that prevents oxidation and keeps the coffee's aroma intact for months, even years. Meanwhile, the caps are screwed on and labels applied by robotic arms that work in perfect rhythm. The printed labels are vivid and glossy, carrying information about roast strength, serving suggestions, and sometimes an image of steaming coffee that seems to rise off the surface. Beneath all that marketing lies an astonishing choreography of mechanical precision. Each jar is scanned for correct fill level and seal integrity. Any container that doesn't meet the standard, even slightly, is automatically diverted off the line with a gentle push of air. Nothing is left to chance. As the packaged jars move toward the end of the line, they pass through metal detectors and X-ray scanners to ensure no foreign material has found its way inside. The instant coffee industry runs under strict food safety standards. Cleanliness is absolute. Workers on the floor wear hairnets, gloves, and anti-static coats. Shoes pass through disinfectant baths. The noise level is high. The hiss of air jets, the hum of conveyors, the whir of vacuum pumps. But there's a sense of calm precision in the movement, like watching a perfectly timed dance. The filled jars are packed into cardboard trays, shrink-wrapped in plastic film, and palletized by automated stacking machines that build tall, stable towers of product, ready for shipment. Forklifts glide between the aisles, guided by sensors that follow magnetic strips embedded in the floor. The entire process is digitized. A central control system tracks each batch from roasting to packaging, logging temperature readings, weight data, and timestamps in real time. In modern facilities, there's almost as much computing power as mechanical energy. Beyond the factory floor, in climate-controlled warehouses, these pallets wait to be distributed to markets around the world. The smell of roasted coffee hangs faintly even here, absorbed into the air and cardboard. Depending on destination, the coffee might travel by truck, by ship, or even by rail, stored in sealed containers that protect it from humidity and temperature changes. The logistics side of instant coffee is as intricate as its manufacturing. Global networks of suppliers, packaging plants, and distributors ensuring that a jar made in one corner of the world can sit on a supermarket shelf thousands of kilometers away, ready to meet its moment with a kettle and a mug. But inside every jar, the coffee is sleeping, waiting for heat to bring it back to life. Those tiny granules, though seemingly dry and inert, are full of preserved aroma molecules and flavor compounds frozen in place by science. When hot water touches them, the reaction is almost immediate. The crystals dissolve, releasing steam that smells like a cafe on a rainy morning. This is the miracle of solubility, engineered through careful control of drying and granule structure, the culmination of every step that came before. Behind the simplicity of that moment lies a staggering amount of engineering. The spray drying towers that create powdery clouds of coffee are as tall as apartment buildings. The vacuum systems that handle freeze drying can maintain temperatures below -40 degrees Celsius while sucking vapor out of solid ice. The extraction systems operate under pressures strong enough to drive water through steel filters dozens of times a day without faltering. Even the simplest factory is a miniature city of pipes, valves, sensors, and conveyor belts, all humming together in quiet synchrony. And yet, for all that machinery, the process still feels profoundly human. It's built on centuries of coffee culture, from Ethiopian highlands to European cafes, refined through the language of chemistry and industrial design. The people who run the machines, who check the gauges and test the samples, are caretakers of that heritage. They make sure that what ends up in the jar still carries the warmth and familiarity of the drink that started it all. The scale is almost difficult to grasp. A single large plant can produce tens of tons of instant coffee per day, enough to fill millions of cups. The waste heat from one roasting unit might be reused to preheat incoming air for another, part of an elaborate energy recovery system designed to make the process more sustainable. Water used in extraction is filtered and recycled through closed-loop circuits. Even the coffee aroma captured during processing is collected, condensed, and reincorporated rather than vented away. Nothing is wasted if it can be saved, because every molecule of flavor has value. And somewhere near the end of the line, where finished jars roll past in an endless stream, there's usually a point where an operator stands, lifting one at random, twisting the cap, and taking in that first whiff. A rich, roasted scent that's the signature of success. In that instant, the long journey from green bean to golden crystal comes full circle. The machines might have done the heavy lifting, but the decision to approve that scent, that balance, that recognizable note of coffee, rests with a human sense of smell trained over years. Inside the instant coffee factory, even after the product is packaged and ready for shipment, the operation never really stops, because every hour of every day, there are systems quietly running in the background to ensure the entire process stays consistent, efficient, and safe. The heart of this invisible network is a combination of sensors and data systems that record everything, from the temperature of roasting air to the humidity levels in the storage rooms. And this real-time monitoring allows engineers to trace every jar of coffee back through its entire production history, identifying which batch of beans it came from, which roaster handled it, and which extraction columns brewed it, creating a traceability map so detailed that if a single inconsistency appears, they can pinpoint the exact moment it occurred. This kind of control is essential because instant coffee is a product that lives or dies on uniformity. Consumers expect it to taste exactly the same, whether they open a jar in Tokyo, Sao Paulo, or Berlin. And achieving that requires not only advanced technology, but also a deep understanding of chemistry and sensory behavior. Inside the quality labs, analysts don't just taste the coffee. They study it at a molecular level, using gas chromatography to measure volatile compounds, spectrometers to check color values, and precise moisture analyzers to confirm stability. The goal is to ensure that each crystal has the same composition of sugars, acids, and aromatic oils, all locked in place and protected from oxidation by the drying process. The science of aroma is one of the most challenging parts of coffee manufacturing. The smell of coffee, that complex mix of hundreds of volatile molecules, is fragile. Many of those molecules begin breaking down the moment they're exposed to air. During extraction, factories often capture these vapors by condensing them into a cold liquid, known as coffee aroma concentrate. Stored at sub-zero temperatures, this concentrate is later sprayed onto the dried granules just before packaging, reintroducing the very aromas that might have been lost earlier. The process requires split-second timing. If the vapor is captured too early or too late, the balance of notes, smoky, fruity, caramel-like, will shift. The aroma concentrate is like the perfume of coffee, distilled from its own breath, and returning it to the granules gives the final product a smell that feels fresh and familiar when the jar is opened. Energy management is another hidden marvel of instant coffee production. The entire process, from roasting to freeze drying, consumes huge amounts of heat and power, and modern plants are designed like closed ecosystems to minimize waste. The hot air that leaves the roasting drums doesn't simply vanish into the atmosphere. It's filtered, cooled, and redirected through heat exchangers that warm up incoming air for the next roast. Water used during extraction is cleaned, filtered, and reused in a cycle that reduces both waste and cost. In some facilities, the biomass from coffee husks and spent grounds is burned in boilers that generate steam to power the plant, turning what would have been waste into renewable fuel. The hum of machinery and the rhythm of conveyor belts mask this elegant web of resource efficiency, a quiet ballet of physics and sustainability that keeps the process balanced. The freeze-drying units are perhaps the most impressive machines in the entire operation. Enormous metal chambers that look like futuristic capsules. Inside, the temperature drops to extremes, pues sometimes below minus 40 degrees Celsius, while powerful vacuum pumps lower the pressure so that ice crystals inside the frozen coffee slabs sublimate directly into vapor. This process can take several hours, sometimes an entire day, as the ice disappears without ever melting. Technicians peer through small circular windows, watching as the color of the slabs slowly changes from dull brown to a lighter, matte texture, signaling that the drying is complete. What remains is a delicate matrix of porous granules, each one preserving the flavor compounds with remarkable precision. When handled, they feel slightly brittle, almost airy, as though holding concentrated fragrance in solid form. Once these granules are collected, they're sieved to remove dust and uniformize the size before heading toward agglomeration and packaging. And every movement from this point on happens in sealed pipes that keep oxygen out. Even the lighting in some areas is carefully chosen because ultraviolet light can degrade certain aromatic molecules. The air smells faintly roasted everywhere, even after multiple filtration systems, a constant reminder of the product's potency. It's said that workers in such plants often lose sensitivity to the smell of coffee after years of exposure, yet visitors are usually overwhelmed within minutes, their senses flooded by the richness of it. Beyond the production floor, there's another world, the research and development labs, where food scientists and flavor engineers work on improving the product. Instant coffee might seem like a finished invention, but innovation never stops. In one corner, a group might be experimenting with microencapsulation, a technique that traps volatile coffee oils inside tiny edible shells to protect them from oxygen and light. In another, chemists test new drying parameters that could preserve more delicate floral notes, often lost in high heat drying. Some teams work on decaffeination methods that maintain full flavor without bitterness, while others study how small variations in grind size can change extraction efficiency by fractions of a percent, which when scaled up could mean tons of coffee saved each year. Every discovery is documented, tested, and often fed back into production lines gradually, each improvement folded seamlessly into the next batch. On the sensory side, professional tasters known as cuppers hold daily sessions. They sit before long tables lined with identical cups of reconstituted instant coffee, each brewed under strictly identical conditions. Same temperature, same water to powder ratio, same stir time. The room is silent except for the sound of spoons dipping, liquid slurped noisily across the tongue, and quiet scribbling of notes. The tasters look for texture, clarity, and aroma retention, and they can detect subtle shifts invisible to instruments, a slightly flatter finish, a hint of extra acidity, an aroma that lingers half a second longer than it should. Their job is part science, part art, and their feedback shapes future production adjustments. In many factories, the sensory evaluation area sits right next to the control room, allowing technicians to tweak variables in real time. If a batch shows faintly over-roasted notes, the roasting temperature curve can be adjusted immediately for the next run. If solubility seems too slow, the granule size distribution might be recalibrated. Every decision is made quickly, and the data from each change is stored digitally, forming part of the plant's memory, a living database of taste. Meanwhile, the packaging systems continue their ceaseless rhythm. Jars clink softly as they move on stainless steel conveyors, the labels spinning onto their surfaces with perfect alignment. Some lines fill small, single-serve sachets, thin packets that must be precisely sealed to prevent moisture intrusion. The machines run at astonishing speed, cutting, filling, and sealing hundreds of sachets per minute in a blur of movement. The air around them is cooler, drier, and filtered to near sterility. Even the human workers enter through air showers that blow away lint and dust. Inside this space, the focus on cleanliness borders on surgical. In warehouses, towering stacks of packaged coffee sit under steady air circulation, waiting for distribution. The logistics systems coordinate shipments so that stock rotates continuously, with the freshest product always moving first. Each pallet is barcoded, each shipment traceable through digital ledgers that connect to retail distribution centers worldwide. From there, the jars and packets disperse into the world, into cafes, hotel minibars, office pantries, and supermarket shelves, carrying within them the work of hundreds of people and the quiet power of thousands of machines. When all these layers of complexity finally meet a single act, a spoon dipping into a jar, granules tumbling into a cup, and hot water poured over them, the speed of transformation hides the depth behind it. The granules fizz slightly as they dissolve, a faint hiss rising before the aroma blooms. It's a moment that lasts only seconds, but it's built upon weeks of engineering, months of harvest, and years of refinement. Every sip connects back to that long, precise chain of creation, from the green slopes where the coffee grew to the cold, vacuum chambers where it was crystallized. It all begins with the peanuts. While it might seem obvious that a peanut butter cup would start with peanuts, what's not widely known is just how much control and specificity Hershey applies to this ingredient before it ever reaches the cup itself. Reese's production lines require massive quantities of peanuts, hundreds of tons per week across facilities, and not just any peanut will do. The factory demands high oleic runner peanuts, most commonly sourced from farms in Georgia, Alabama, and Texas. These peanuts are preferred for their uniform kernel size, mild flavor, and high oil content, which delivers a creamier peanut butter base. Once harvested, peanuts are sent to dedicated shelling and blanching facilities, where they are cleaned, sorted, and skinned. The outer red skins are removed through dry abrasion, and the kernels are visually and electronically inspected to eliminate any with defects, mold, or foreign materials. Only the highest grade peanuts, typically designated as US Fancy or US Extra Large, are accepted for Reese's production. These peanuts are then loaded into food-grade hoppers and shipped in sealed bulk containers to the peanut butter manufacturing lines at Hershey's centralized processing plants. Upon arrival at the factory, the peanuts are stored in stainless steel silos within a climate-controlled environment to prevent spoilage. Prior to use, the peanuts are metered into roasting drums. Roasting is a critical step not just for flavor, but for aroma development and moisture reduction. High-capacity rotary roasters or continuous conveyor-style roasters are used, depending on the factory's line design. Peanuts are typically roasted at temperatures between 320 degrees Fahrenheit and 360 degrees Fahrenheit for 30 to 45 minutes. The exact temperature curve is adjusted based on peanut moisture and oil content, which is sampled batch by batch in the factory's lab using gas chromatography and moisture analyzers. The roasters are equipped with air impingement systems and inline sensors to monitor internal temperature, color, and roast development in real time. At various intervals, small test samples are pulled using auto draws for taste panel review. Roast level has to be absolutely consistent, as this is the foundation for the signature Reese's peanut butter flavor. Over-roasted peanuts will produce a burnt or overly bitter taste, while under-roasting leaves the flavor bland and oily. Once roasted, peanuts are cooled using high-powered air chillers to prevent overcooking and to stabilize the oils. They are then conveyed into degermers and mechanical splitters, where they are cracked open and the hearts, the hard inner core of the peanut, are removed. These hearts, while technically edible, can impart a bitter or chalky aftertaste, so they are separated out and typically used in livestock feed or secondary food processing streams. Now comes the grinding phase. The roasted and cooled peanuts are fed into large, high-shear grinders, industrial versions of what's used in commercial peanut butter production. These grinders operate at extremely high RPMs and are often configured in a two-stage system: a coarse grind followed by a fine grind. In the coarse phase, the peanuts are broken down into a grainy paste, preserving small particulates that contribute to the slightly gritty texture of Reese's peanut butter. This paste is then piped into a second mill, where it's refined to a smooth, uniform consistency. The peanut paste is blended in stainless steel mixing tanks equipped with variable speed paddles and heated jackets. At this stage, a proprietary mix of additional ingredients is incorporated. These include salt, sugar, a small amount of fully hydrogenated vegetable oil, and a dry milk derivative. The sugar used is finely milled and sieved to a consistent particle size, ensuring it disperses evenly throughout the mix without recrystallizing. Emulsifiers such as mono and diglycerides are added in microdoses, enabling the fat and protein phases to remain homogeneous over time. What makes Reese's filling unique, and one of the factory's guarded secrets, is its texture. It isn't traditional creamy peanut butter. It's dry and crumbly, almost fudge-like, but melts smoothly on the tongue. This is achieved by very specific moisture and fat content targets. The factory carefully controls the fat ratio in the peanut blend using inline nuclear magnetic resonance sensors, which measure fat levels without destroying samples. The ideal balance results in a pliable, moldable filling that holds its shape during chocolate enrobing but softens under bite pressure. Once blended, the peanut butter filling is pumped into chilled hoppers and held at precise temperature, typically between 60 degrees Fahrenheit and 70 degrees Fahrenheit, so it can be extruded or deposited with exact weight and shape control. Temperature consistency is crucial here. Too warm, and the filling becomes too soft and spreads when deposited. Too cold, and it hardens and resists clean shaping, risking damage to the chocolate cup. The final stage in this first segment is the formation of the peanut butter centers. On a separate production line, the cooled peanut filling is portioned using servo-driven pistons or extrusion rollers, depending on the cup format being produced. These machines deposit small, perfectly measured mounds of filling onto a chilled conveyor. In larger cups, the filling is puck-shaped. In minis, it's closer to a small dome. Each peanut butter deposit is then transferred into a temporary holding tunnel, essentially a refrigeration corridor, where the shaped fillings are stabilized prior to the chocolate enrobing phase. Here, humidity and temperature are carefully balanced to avoid condensation or fat bloom when chocolate is later applied. At this point, the peanut butter centers are firm, uniform in size and shape, and fully ready for the next critical phase of the process, chocolate molding. With the peanut butter centers now precisely formed, cooled, and stabilized, the next critical phase in the industrial production of Reese's peanut butter cups begins: chocolate shell creation and cup assembly. This portion of the process is all about precision, timing, and the seamless integration of multiple complex systems to produce a product that's visually perfect and texturally balanced. It's here that the familiar cup shape begins to take form, and where Hershey's decades of manufacturing expertise are on full display. The chocolate used in Reese's products is developed in-house and differs slightly from that used in a Hershey's milk chocolate bar. While it still contains cocoa solids, cocoa butter, milk solids, sugar, and lecithin, it has been tailored specifically to pair with the salty sweet peanut butter filling. The chocolate is slightly softer in melt, less bitter than dark chocolate, and has a fat and sugar profile that ensures it doesn't overpower the filling. It's formulated to be both moldable and stable under typical shelf conditions, even in warmer climates. The chocolate arrives at the cup production line in a liquid state, held in large tempering tanks kept at a precise temperature, usually around 30 to 32 degrees Celsius for milk chocolate. Tempering is an essential part of chocolate manufacturing and involves heating the chocolate to fully melt its cocoa butter crystals, cooling it to initiate the formation of stable type 5 crystals, then gently reheating it to bring it to working temperature. This process ensures that once the chocolate is set, it has a glossy finish, resists bloom, and has a clean snap when broken. The first step in forming the Reese's cup is lining the signature brown paper cup mold with chocolate. The production line is fed with pre-formed paper cups stored in large reels or stacked columns that are automatically dispensed onto a high-speed conveyor. These paper cups are food grade, waxed, or coated with a thin moisture barrier and shaped precisely to hold their structure during and after chocolate deposition. Once the paper cups are set in place on the moving line, a chocolate depositor head releases a measured dose of tempered chocolate into each one. This is known as the bottoming phase. The amount of chocolate is critical, not only for structure, but also for controlling the ratio of chocolate to filling. After deposition, the cups pass over a vibration table. This stage is crucial for evenly spreading the chocolate along the bottom and slightly up the sides of the paper cup. The vibration table uses rapid, controlled pulses to remove air bubbles and to ensure a uniform shell that won't crack or collapse during filling. Immediately following the bottoming step, the peanut butter centers are dropped into the liquid chocolate. These centers have been transferred from the refrigerated holding tunnel to the enrobing line and are picked and placed with robotic arms or pneumatic suction systems that gently lower each piece into its corresponding chocolate-lined cup. The timing of this placement is perfectly synchronized so that the peanut butter slightly sinks into the chocolate but doesn't hit the bottom, allowing a chocolate base to remain intact beneath the filling. As the peanut butter sits in the base, a second dose of chocolate is deposited on top. This is referred to as the capping phase. The capping head delivers another precise amount of tempered chocolate to completely enrobe the peanut butter core. This top layer seals the filling, ensuring the product is fully enclosed and protected from oxygen, moisture, and contamination. The final thickness of the cap is carefully calibrated so the chocolate shell is strong enough to hold shape, but still soft enough to bite through easily without excessive crumbling. The assembled cups, now complete with base, filling, and cap, are conveyed into a long, multi-zone cooling tunnel. These tunnels are often 20 to 30 meters in length and feature graduated temperature zones, starting at around 16 degrees Celsius and dropping to 8 to 10 degrees Celsius toward the end. The slow, controlled cooling is essential to prevent condensation or stress fractures in the chocolate. Too rapid a chill can cause bloom or cracking, while uneven cooling can result in misshapen edges or textural inconsistency. Inside the cooling tunnel, conditioned air circulates in laminar flow patterns, ensuring that every cup is exposed to identical cooling conditions. The duration of the tunnel cycle is calibrated to match line speed and product size. Larger Reese's big cups may require longer chill times compared to the classic or miniature versions. At the tunnel exit, the cups are inspected by automated vision systems that detect anomalies like off-center fillings, insufficient chocolate coverage, or edge deformation. Any defective cups are automatically diverted from the line for reprocessing. The cups that pass inspection are ready for packaging. But before that happens, there's one last critical test: weight and sealing verification. Inline check weighers use load cells to weigh each cup or group of cups to ensure they fall within designated tolerances. Simultaneously, barcode scanners and optical sensors check that each product is aligned and properly seated in its paper cup. The final stage before wrapping is an air dusting system that removes chocolate crumbs, static particles, or paper fragments from the surface to ensure a clean, polished presentation in the final package. Packaging of Reese's cups is a high-speed operation. Cups are grouped automatically into configurations appropriate for each product format: singles, twin packs, snack-size multi-packs, or seasonal variations. Each group is loaded into a continuous film wrapping machine, which pulls branded plastic film from a roll, wraps it around the cups, seals it with a heated crimper, and cuts it into individual packages. The film is pre-printed with product information, UPC codes, and freshness dates that were applied earlier by industrial flexographic printers. Once wrapped, the products pass through another metal detector or X-ray system to detect any foreign contamination that may have occurred during packaging, a standard in modern food manufacturing. Any anomaly results in immediate ejection and shutdown of the machine until the issue is resolved. The acceptable product continues to cartoning lines, where it is packed into retail-ready boxes, display trays, or bulk shipping cases depending on the destination. Finished product cartons are coded, palletized by robotic stackers, and shrink-wrapped for transport. Each pallet is labeled with a unique tracking number that links it to its production batch, shift number, ingredient lot codes, and quality control logs. This traceability allows for quick response in case of any issues in the supply chain. Every Reese's peanut butter cup batch is subject to a comprehensive quality assurance protocol from start to finish. While visual inspection, weight checking, and foreign material detection handle surface-level defects, deeper analytical testing is performed regularly throughout production. Factory labs adjacent to the production floor run hourly tests on product samples pulled from the line. These tests measure water activity, pH levels in the peanut filling, chocolate temper index, fat content, and emulsifier concentration. Advanced equipment like near-infrared spectrometers and gas chromatographs are used to validate these metrics with precision. In addition to instrument-based testing, trained sensory panels perform blind evaluations of finished product samples. These panels, often composed of factory employees specially trained in flavor and texture recognition, assess everything from peanut aroma intensity to shell firmness, sugar balance, and mouthfeel contrast between chocolate and filling. Feedback from these panels is compared to golden standard benchmarks. Reference Reese's cups produced under ideal conditions that are stored in temperature and humidity-controlled archives. These control cups are regularly reviewed to ensure no drift in product quality over time. Allergen control is one of the most sophisticated systems running silently beneath the surface of Reese's production. Since peanuts and dairy are both major allergens, Hershey facilities that manufacture Reese's operate under strict protocols to prevent cross-contamination. Separate ingredient receiving docks, isolated storage silos, color-coded tool systems, and dedicated air handling zones are used to segregate peanut-related materials from other production lines within the same facility. Sanitation crews follow clean-in-place procedures using food-safe alkaline and acid-based cleaners to remove all traces of allergens between product changeovers. Swab testing for peanut protein residue is conducted on all contact surfaces before production resumes. Hershey also enforces supplier controls. All incoming peanut shipments are tested for aflatoxins, a class of toxic compounds produced by certain molds that can occur in improperly stored peanuts. Only peanuts that pass stringent safety thresholds are accepted, and each delivery is logged and tracked using batch codes that link to the final product's traceability system. This digital record keeping allows Hershey to track every ingredient back to its source farm and forward through every unit sold. But Reese's isn't just a singular product anymore. Over the years, the brand has expanded into dozens of variations: white chocolate cups, dark chocolate, big cups, miniatures, stuffed versions with pretzels, potato chips, Reese's Pieces, or caramel. Each variant requires its own unique processing conditions and introduces new complexity to the factory system. Let's take the white chocolate Reese's as an example. This variation uses a cocoa butter-based confectionery coating rather than traditional milk chocolate. It must be handled in separate melters and tempering systems due to its sensitivity to high heat and faster tendency to bloom. White chocolate also requires precise control of ambient light and humidity during production and packaging, as it is more susceptible to visual imperfections. On the line, switching from standard milk chocolate to white chocolate triggers a full line cleaning and recalibration of depositor and cooler settings. Flavor variants with inclusions, like Reese's with Reese's Pieces inside, add another layer of complexity. In these formats, the peanut butter filling is first blended with the inclusion, pieces, chips, or even candy bits, using slow-speed paddle mixers to avoid crushing or melting the added components. These inclusions alter the viscosity and extrusion behavior of the filling, requiring depositor nozzles to be widened and dosing pumps to be recalibrated for accurate weight control. Additionally, because candy-coated pieces can crack or leak color when exposed to oil migration from the peanut butter, the storage conditions of these fillings must be tightly managed to preserve structural integrity during molding. Even packaging formats are adapted. Big cups, which contain more filling and sometimes additional elements, require thicker paper cups and slightly wider flow wrapping machines to handle the larger size. Seasonal versions, like pumpkin-shaped Reese's for Halloween or tree-shaped cups for Christmas, require completely new mold tooling, reshaped paper cups, and different wrapping film dimensions. These seasonal SKUs are often produced in limited time production runs scheduled between mainline batches, with precise coordination between departments to minimize downtime and clean out inefficiencies. To manage this growing complexity, Hershey's manufacturing ecosystem is deeply integrated with real-time data and automation. Programmable logic controllers govern every stage of production, from peanut grinding to chocolate capping. These controllers constantly adjust conveyor speeds, depositor volumes, oven temperatures, and cooling rates to match product specifications in real time. Sensors along the line feed back information on humidity, belt tension, machine vibration, and material flow. If any parameter drifts beyond the preset tolerance window, an alert is triggered immediately and logged by the manufacturing execution system. The MES serves as the brain of the operation. It logs every batch, shift, operator, ingredient lot, and test result. It manages production schedules based on demand forecasting from Hershey's enterprise planning systems, and it ensures the right packaging, ingredients, and machines are prepared for the next product variation before the current one is even complete. The MES also interfaces with digital traceability systems, allowing Hershey to execute complete recalls if necessary, though this is extremely rare due to the redundant safety nets in place. To support sustainability goals, the factory also measures key environmental metrics. Energy usage from roasting, tempering, and cooling operations is tracked and optimized. Waste heat from roasters is sometimes redirected to preheat water for sanitation systems. Chocolate scrap from edge trimmings and overflows is collected and reworked in designated reclaim tanks. Even the cardboard used for cartons and paper used for wrapping is sourced from certified sustainable forestry programs. Water used in cooling tunnels is recirculated through industrial-grade filtration systems and UV sterilization loops, allowing for multiple reuse cycles before any disposal. Factory roofs are often equipped with solar panels, contributing to the site's renewable energy footprint. These sustainability measures not only support Hershey's corporate goals, they also help reduce operating costs and ensure compliance with international environmental standards, especially for exports to markets with strict eco-regulations. Finally, at the distribution level, finished pallets of Reese's are scanned, shrink-wrapped, and entered into a dynamic warehousing system. Pallet storage is optimized by weight, sell-by date, and destination zone. Reese's products are shipped in refrigerated trucks when needed, although standard varieties are stable at room temperature due to their low water activity and solid fat matrix. Shipments are tracked via GPS and load sensors to ensure they remain within safe handling conditions throughout transit. So when you open a Reese's peanut butter cup and experience the snap of chocolate, the softness of the peanut filling, and the perfectly even texture from edge to edge, what you're actually tasting is the output of a meticulously engineered, continuously monitored, and relentlessly optimized factory system. Behind every wrapper is a chain of roasting drums, tempering tanks, vibration tables, chilled tunnels, microlab samplers, PLCs, conveyors, AI sensors, and hundreds of trained hands working in quiet unison to make every bite familiar, reliable, and timeless. As Reese's peanut butter cups leave the controlled environment of production and are loaded onto outbound trucks, the story doesn't end with the last machine seal or pallet scan. In fact, one of the most underappreciated aspects of the manufacturing system lies in how Reese's maintains product integrity far beyond the factory walls. The journey from factory to store shelf, and ultimately to the consumer's hand, is an extension of the manufacturing process itself. For a product like Reese's, where texture, flavor, and structure are so carefully engineered, maintaining those qualities through shipping, storage, and retail presentation is non-negotiable. Temperature control plays a key role in this extended quality assurance chain. While Reese's peanut butter cups are classified as shelf-stable and do not require refrigeration, they are extremely sensitive to heat and humidity. Elevated temperatures can cause the chocolate to melt or bloom, a condition where cocoa butter rises to the surface and creates a whitish-grey coating. Though harmless, bloom gives the appearance of staleness or spoilage and is unacceptable in any retail-facing product. To prevent this, shipping containers and trucks are monitored using digital temperature loggers and GPS trackers. These devices not only ensure compliance with storage requirements, but also provide real-time alerts if conditions fall outside predefined thresholds. Warehousing and retail logistics are optimized with similar care. Distribution centers receiving Reese's shipments are instructed to rotate inventory on a strict first-in, first-out system to preserve freshness. Shelving time is tracked down to the day, with expiration dates digitally logged and printed clearly on all packaging. Retailers are often supplied with merchandising guidelines from Hershey's sales and operations teams, advising on optimal product placement to avoid heat sources and maintain visibility in high-traffic zones. This ensures not just product survival, but also consumer engagement. Meanwhile, Hershey's central data systems stay connected to the broader supply chain. Sales velocities from thousands of retail points are monitored using automated inventory systems that integrate with distribution algorithms. If Reese's products are selling faster than expected in one region, perhaps due to a seasonal promotion or viral social media trend, production forecasts and shipment routes are adjusted in near real time to prevent outages. Conversely, if stock is underperforming, the system can slow production or reroute product to a region with higher demand. But what truly sets Reese's apart in this final segment of its manufacturing cycle is its flexibility for innovation and customization, especially on a global scale. Reese's peanut butter cups aren't manufactured identically across every country. Although the core elements remain the same, formulations may be slightly adjusted to meet regional preferences, regulatory standards, or ingredient availability. For example, Reese's produced for the European market may contain non-GMO ingredients or use different emulsifiers to comply with EU food safety regulations. Sugar content, fat ratios, and even packaging inks are tailored to local markets, and each international facility must pass regional audits to ensure compliance with both Hershey's standards and those of the target nation. Seasonal and limited edition Reese's lines introduce another layer of production complexity that extends into post-factory strategy. Every year, variations such as pumpkin-shaped Reese's in October, tree-shaped ones in December, and heart-shaped versions for Valentine's Day hit the shelves. These products require not only physical retooling, custom molds, unique wrappers, modified flow wrappers, but also adjusted production timelines to accommodate pre-holiday distribution. Most holiday variants are produced months in advance to ensure they hit retail shelves in time for the season, but remain fresh through the actual holiday window. To ensure holiday versions meet the same performance standards as core SKUs, Hershey uses accelerated shelf life testing. In these tests, products are stored at elevated temperatures and humidity for a condensed time frame to simulate long-term storage. The samples are then analyzed for fat migration, filling breakdown, wrapper integrity, and flavor degradation. Only those variants that meet Reese's strict internal benchmarks for shelf life, texture stability, and visual appearance are approved for full-scale seasonal release.